Um, let's start. Distinguished participants, expert speakers, colleagues from our partner organizations, ladies and gentlemen, good afternoon or good morning, depending on the local time in your country. On behalf of the Secretariat of the Capacity Development Program on Air Quality Management and Emission Reduction of PM 2.5 for Asian countries, I would like to extend our warm welcome to all of you. Thank you for joining this capacity building workshop. Kindly allow me to introduce myself. My name is R.L. Verma. I am coordinating the Air Quality Management Capacity Development Program at the Regional Resource Center for Asia and the Pacific, Asian Institute of Technology, AIT RRC.AP. I will moderate all the sessions of this workshop and learn together with you the various aspects of the air quality management. Now, I would like to invite Dr. Naoya Tsukamoto, Director of the Regional Resource Center for Asia and the Pacific, Asian Institute of Technology, Bangkok, Thailand, to deliver the welcome remarks. Dr. Tsukamoto, the floor is yours.
Thank you. Thank you very much, Verma. Dr. Monchip Sritana Tapkianon, Senior Advisor to the National Research Council of Thailand, former Director of the Environmental Research and Training Center, and Deputy Permanent Secretary, Ministry of Natural Resource and Environment, Thailand. Mr. Yoichi Toyama, Director, Asia Pacific Network for Global Change Research, APN Secretariat. Professor Mario Tapkianon, Emeritus Professor of AIT, Senior Advisor to the Regional Resource Center for Asia and the Pacific. Distinguished resource persons, participants, colleagues from our partner organizations, and ladies and gentlemen. Good afternoon or good morning to all participants in the world. On behalf of the Regional Resource Center for Asia and the Pacific, it is my great pleasure and honor to welcome you to all this capacity development program on air quality management and emission reduction of PM 2.5 for Asian countries. It is reported that since December 2019, for 1 year and 9 months, 4.6 million people died because of the COVID-19. Then, let us look at air pollution. UNEP reported that around 92% of people in the world are getting exposed to high levels of air pollution and leading to about 7 million premature deaths each year. Sadly, it has impacted the Asian region the most, with many Asian countries identified as among the topmost polluted cities in the world. In the absence of aggressive intervention, it is predicted that this number could probably double, up by 2050. Recent data on the Air Quality Life Index published by a group of scientists led by the University of Chicago revealed that the change in the life expectancy of people due to the impacts of air pollution is more in the Asian and African countries, where the level of air pollution is high. Based on the Air Quality Life Index data, it is shocking to know that comparing with the WHO guidelines on air quality, the lifespan of the people of South Asia decreased by 5 to 6 years, since the air pollution level there is very high. More or less similar impacts are reported for other parts of the world where air pollution level is high. There is really an urgency to seriously address air pollution issues. More enhanced collective and collaborative efforts and actions among all sectors and stakeholders are necessary to improve air quality. Regional cooperation, strengthening institutions and governance, promoting behavior change, and increasing capacity for integrated air quality management are among the relevant measures to achieve healthy air. Improving air quality will bring health, development, and environmental benefits. A partnership is also a key element. In light of this, we are extremely grateful to APN and the other partners for this opportunity to collaborate in organizing this capacity development program on air quality management and emission reduction of PM2.5 for Asian countries. This training program is hosted to build the capacities of the Asian countries to better manage air quality and enhance technical capabilities to support national efforts to address air pollution issues. This was originally planned to be a face-to-face training, but COVID prevented us from meeting physically. But even though we are conducting this virtually, I'm certain that we can still maximize the learning given the rich experience and experiences of our esteemed experts during whole week. I would like to thank all our distinguished speakers for supporting us in this initiative. And as I understand that we have now close to 300 participants from about 30 countries from Asia and beyond, from various sectors representing governments, NGOs, civil society, and academia. We have actually exceeded our original target of 200 participants. And this is indeed a very good sign that more and more people are now interested and encouraged to contribute to these solutions of this persistent problem or air pollution. I would like to thank you all for taking this step. Lastly, I would like to mention that September 7, 2021 was designated as the International Day of Clean Air in Blue Skies. It has recognized that increasing interest of the international community in clean air and emphasized the need to make further efforts to improve air quality, including reducing air pollution or protect human health. This year, the theme is Healthy Air and Healthy Planet, which emphasized the health aspects of air pollution, especially considering the COVID-19 pandemic. And I would like to echo the message of the UN Secretary General on the observance of the day to quote, "So, today and every day, let us work together to clean the air that we breathe, so we will protect both people and the planet." Thank you so much, and I wish you all a fruitful and successful training workshop this week. Thank you so much for your attention.
Thank you very much, Dr. Tsukamoto, for your welcome remarks. Next, I would like to invite Dr. Montip Siriratna Tabakunan, Senior Advisor to the National Research Council of Thailand, former Director of the Environmental Research and Training Center, Thailand, and former Deputy Permanent Secretary, Ministry of Natural Resources and Environment, Government of Thailand. Unfortunately, she has another engagement at the same time, so she has sent her opening remarks through a video message. May I request my colleague, Mr. Bayasa, to play the video message.
Colleagues, participants, ladies and gentlemen, good day. It gives me great pleasure to speak at the opening of the Capacity Development Program on Air Quality Management and Emission Reduction of PM 2.5 for Asian countries. I commend the organizers led by the Regional Resource Center for Asia and the Pacific, or RRC.AP, of the Asian Institute of Technology, with the generous support of the Asia Pacific Network for Global Change Research, or APN Japan, and all partner organizations for their great efforts in making this program possible. Evolution has become a serious transboundary environmental and health problem globally. As APN National Focal Point for Thailand, and having had opportunities to share concerns with ideas with APN colleagues, I believe that air quality and emission reduction of particulate matter, PM 2.5 in particular, are pressing common concern of countries to protect the health of people and the planet. The holistic transdisciplinary approach to tackling the science and policy issues, as reflected in the comprehensive program content in the terms of monitoring, developing emission inventories, modeling, flows, impact assessment, and policies for mitigation, is responsive to building capacities and competencies of researchers and policymakers. I trust that the knowledge gained in this program will benefit not only the individual participants, but also the organizations you represent and society as a whole. And I wish you a productive program. Thank you.
We are really thankful to Dr. Montif for her opening remark through the video message. Now, next, I would like to invite Mr. Yoichi Toyama, Director of the Secretariat for the Asia Pacific Network for Global Change Research, APN, Japan, to deliver the opening remarks. Mr. Toyama, the floor is yours.
Good morning and good afternoon, everyone. I am Yoichi Toyama, Director of the APN Secretariat located in Kobe, Japan. I'm very pleased to be invited here to deliver an opening remark today. First of all, I'd like to express my gratitude and appreciation to the Director, Dr. Tsukamoto, Dr. Bellman, and all other RRC.AP members and staff of the Asian Institute of Technology to make great efforts in preparing this program. APN Center is established in 1996, and 20 countries in Asia-Pacific regions are members now. Our activities are supported by the contribution from government of Japan, Korea, New Zealand, and Hyogo Prefecture in Japan as well. Our activities are based on the resolution of intergovernmental meetings. We mainly engage in the support of collaborative research projects on global change research and capacity building of early career researchers who engage in these research programs in the Asia-Pacific region. We conducted more than 500 projects since 1996 and more than 1,600 articles generated from those projects. We also assist activities of IPCC, UNFCCC, EPS, etc. indirectly through supporting activities of involved researchers. Japan faced serious situation of environmental pollution during high economic growth era after World War II. Rapid development of heavy industries, motorization, and urbanization caused complicated and wide environmental problems involving various stakeholders. In the struggle against those problems, more lessons accumulated and environmental protection policies developed. We are now facing similar problems in Bangkok, Jakarta, and other megacities in Southeast Asia, as you know. On the other hand, we already know many cases are effective environmental protection policies and pollution control technologies. I think some of those solutions and policy-making process are due to be introduced in the course this way, such as monitoring technologies, risk evaluation, developing indicators, etc. When I joined the Ministry of Environment in Japan, my first job was regulation of risk of various potential air pollutants. I remember that we had to spend plenty of hours to prepare assessment reports. Nowadays, with the assistance of computers, this kind of work has become easier, but risk analysis is still difficult. To decide to what extent the risk of pollutants is acceptable is not only belongs to science but also to psychology. I remember we set 10 minus set, whose power as tolerable for additional cancer occurrence risk and calculate environmental standards for several substances such as benzene and made guidelines for risk reduction. Regarding the dioxin problem, measurement of dioxins need very expensive equipment and rapid manipulation in operation at the early stage. This implies necessity of very complicated policy-making techniques to set measures in the code. I believe that environmental policies will appear in many developing countries in the near future, similar of Japan as industrialization progress. It is said that around 70% of world population will live in cities in the next 30 years. The percentage of the population of Asia is very high. Therefore, I think this trend curve is timely and very meaningful, especially for policymakers, air quality managers, and administrators in pollution control region in Southeast Asia. Air pollution control has been conducted by a combination of various policies and methods. This ground will be very beneficial for the participants to expand their capabilities because this includes valuable lessons accumulated in the history of environmental policies. Participants will be able to learn comprehensive knowledge required for establishing policies in a consistent manner as the basis of understanding other environmental policies. A successful 5-day program seems to be tough, but I believe all of you will do well. I hope this program will help participants to develop their further careers and widen their activities to make a great success. Thank you.
Thank you very much, Mr. Toyama, for your opening remarks. Next, I would like to invite Professor Mario Tabucanon, Senior Advisor to the Regional Resource Center for Asia and the Pacific, Asian Institute of Technology, RRC.AP, AI, to deliver the opening remarks. Professor Tabucanon, the floor is yours.
Thank you very much, Dr. Varma, for the kind introduction. Regional Resource Center for Asia and the Pacific Director, Dr. Naoya Tsukamoto, APN Secretariat Director, Yoichi Toyama, distinguished colleagues, resource persons, participants, I extend my warm greetings to one and all, wherever you may be physically. I am deeply honored and delighted to be with you, and being the last speaker in the opening session, I have the distinct privilege to gratefully echo the words and messages of the previous speakers and join them in extending profound appreciation to all the organizers, partner organizations, resource persons, and participants for making this program possible. There is one thing that I would like to underscore in my brief opening message. I view this capacity development program in a broader context through the lens of the interplay of science, policy, and society. The implementation of the UN 2030 Agenda at the national, subnational, and local levels requires a strong alliance between the scientific and academic community, the government sector, and the multitude of stakeholders in society. The scientific understanding of the economic, environmental, and social dimensions of sustainability and their interlinkages and interrelated emerging issues is crucial to all aspects of the Sustainable Development Goals. Such an understanding assesses gaps and shortfalls in achievement. It informs and revisits policies, which can then motivate science to find solutions for policymaking for the benefit of society. Let's look at this program. This capacity development program on air quality management and emission reduction of particulate matters responds to the calls for strengthening the science, policy, society interface on a real-life pressing problem, and that is air pollution quality, as well as for the identification of the underlying issues through 5 well-defined program modules that the participants will follow through in this program in the next 5 days. Namely, air quality monitoring, inventory modeling, and that's the domain of science. Impact assessment on health, not only on people, but also of ecosystems. That's the societal concern. That's society. And ultimately, mitigation. That's the government sector, and that's policy. So you can see the interplay of science, policy, and society. So to recapitulate, my opening message is that with understanding specialized disciplines, as we should, one should also at the same time be mindful of the holistic, big picture view of issues to enable understanding how science advice can better be integrated into the policymaking process for societal benefits. We must empower science, data and information evidence for knowledge creation, and translate this knowledge into wisdom and smart actions for creating a better quality of life. And to me, that is the roadmap to the future going forward. So I wish one and all who are attending this program a fruitful and productive program this week, and we will see you online in the days ahead. Thank you so very much.
Thank you so much, Professor Tabakonon, for your opening remarks. Now, we have come to the end of the opening session of the workshop. Now, let's take this opportunity to take a group photo. My colleague, Mr. Bayasa, will take a screenshot of the workshop. So may I request all of you to switch on your camera and focus on the camera. I will say 3, 2, 1, and then the screenshot will be taken. Since the number of participants are many, so we will take screenshots 3, 4 times in order to accommodate maximum number of participants. So that's ready. Three, two, one. One more time. One more time. One more time. Okay. Okay, thank you so much. Now I would like to introduce the agenda of the workshop. Can you make this tabakunam? Professor Mario, can you take out your screen? Share? No. Oh yeah, I can still see. I cannot share my file. Okay. Okay. So I'm going to introduce the agenda of this capacity development program on air quality management and emission reduction of PM 2.5 for Asian countries. My name is R.L. Verma. I'm coordinator of this air quality management capacity development program at AIT RRC.AP. The main objective of this capacity building workshop is to build the capacity of the Asian countries on air quality management and emission reduction of PM 2.5. The sub-objectives are to develop capacity on air quality monitoring. Second, to develop capacity on emission inventory development and emission tools. And the third, to develop capacity on air quality modeling. Fourth, to develop capacity on air pollution impact assessment. And the fifth, to develop capacity on emission reduction policies and action plans. So there will be 5 modules for this whole duration of workshop. One is air quality monitoring, and the second one is model 2 is emission inventory development. Module 3, air quality modeling. Module 4, impact assessment, and module 5, air pollution mitigation policies. So on day 1, that means today, September 13, from 13:30 to 17:30, we will have 4 presentations from very renowned speakers of the Asian countries or around the world. So the presentation 1 will be on overview and importance of air quality monitoring for air quality management, Professor Kimon from AIT. And then presentation 2 will be from SN Tripathi from Kanpur, IIT Kanpur, on air quality monitoring using the low-cost sensor. Third presentation will be from Professor Mohammad Bilal, NUIST, Nanjing, China, on air quality monitoring using the satellite. And the fourth presentation will be from Dr. Sirikarn Leung Sakul, Department of Industrial Works, Thailand. On day 2, we will have 3 presentations that will start from 13 hours to will end 16 hours. And in module 2, that is the emission inventory development, we will have 3 presentations. Presentation 5th or 1 for the second day is from Dr. Ikbordin Vinikudul, AIT, Thailand, on overview of emission inventory development process and emission factors. Presentation on module 2. The second presentation will be from Dr. Didin Augustine Paramadi from ITENS, Indonesia. And the fourth presentation or the third presentation of the day, of the second day, will be from Dr. Muhammad Firoz Khan, University of Malaya, Malaysia, on source apportionment of emissions of air pollutants. On day 3, that is module 3, air quality modeling, there will be 3 presentations. Presentation 1 and 2 on day 3 will be from Dr. Bhupesh Adhikari, EC Mode, Nepal, on overview of air quality modeling and application of chemical transport model and photochemical models in air quality management. And the third presentation of the module 3 will be from Dr. Sakda T. Dech from Pollution Control Department, Thailand, on air pollution forecasting with focus on PM 2.5. On day 4, there will be 3 presentations. Presentation 1 from Dr. Pechavardi Suwantada, sorry for my mispronunciation, Pollution Control Department, Thailand, on overview of air pollution impact assessment. Then presentation 2 of the day 4 is from T.W. or J.W. Wong. T.W. Wong, Professor T.W. Wong from the Chinese University of Hong Kong. And the third presentation of day 4 will be from Dr. Eric Jusman, IGS, Japan, on co-benefits of air pollutant emission reduction. On day 5, it is a very long session. So we will have the 5 presentations. The first presentation from on day 5, that is the air pollution mitigation policies module, is from Miss Gilinda Baterina from Clean Air Asia on perspective on air pollution mitigation strategies and action plan in Asia. Presentation 2 on day 5 will be from Toshihiko Takemura, Kyushu University, Japan, on linkages, air pollution linkage, and air pollution and climate change linkages. And the third presentation of day 5 is from Dr. John C.I. Kulistivinia from SCI, UK, on long-range energy alternatives planning integrated benefits calculator, that is LEAP IBC. The fourth presentation on module 5 will be from Miss Maria Caterina Paddo from UNEP ROAP on clean air measures for Asia Pacific region. The last presentation on day 5 will be from Mr. Sundeep Singh, Ministry of Environment and Climate Change, India, on National Clean Air Program of India. And then after the this all 5 the days, an evaluation of the participants will be made through an online survey in order to measure enhancement in the knowledge and understanding of participants. For each topic of the lecture, a set of questions is prepared to get the response from the participants. Write 5 key points you learned from this lecture is a key question to answer for evaluation. Participants are encouraged to attend every lecture and provide the feedbacks. A certificate of participation, soft copy, will be awarded to those who will successfully submit their evaluation within the deadline. And the evaluation form already uploaded on the website, and the deadline of the submission of evaluation is 27 September 2021. That is 10 days from the end of the workshop. So thank you so much, and let's learn together. Bahasa. Still there. Okay. Now let's start the workshop presentation. However, before we start the presentations, may I request all the participants to mute your microphone and switch off your camera to avoid any disturbance in the streaming of the workshop proceedings. May I also request the speakers to finish your presentation within 45 to 50 minutes so that the participants will have 10 to 15 minutes for Q&A. Participants are requested to type your questions in the chat box, and I will convey your questions to speaker for the answer. If you want to ask more questions and if the time does not permit, please send your questions to me by email. I will request the speaker to reply you later. The first module of the workshop is air quality monitoring, and there will be 4 presentations in this module, and all presentations is likely to end at 5:30 p.m. Thailand Standard Time. So the first presentation of the air quality monitoring module is an overview and importance of ambient air quality monitoring for air quality management by Professor Kim On from School of Environment Resources and Development, Asian Institute of Technology, Thailand. Professor Kim is a member of the science panel of the Asia Pacific Clean Air Partnership, that is APCAP. She has more than 35 years of experience in research and education and consultancy and capacity building. Professor Kim is internationally recognized for her work on air pollution and climate in Asia. She spent untiring efforts to provide a better understanding or characterization of air pollution issues in Asian developing countries through field measurements, emission inventory, modeling studies at urban, national, and regional scale level. She has published 2 books and over 110 research papers, 50 books and 50 book chapters, and 50 development reports. She has conducted as PI and co-PI over 50 regional collaboration research projects and supervised over 190 master and 16 PhD students. Professor Kim got several awards and prizes, including International Best Journal Paper Awards, recognition from Better Air Quality Conferences. So, Professor Kim, the floor is yours. Professor Kim, you are muted. Professor Kim, we cannot hear you. Can you unmute?
Okay. Can you see my screen?
Yeah, we can hear also, but we cannot see your presentation.
You cannot see my presentation now?
Yeah, we can see now.
Okay. Okay.
Make it full screen.
Yes, right.
Yeah,
Okay.
that's true.
Good afternoon, everyone. Can you hear me clearly?
Yeah, we can hear you.
Okay, we are around 6 minutes late, so my lecture, I try to shorten it, but I'm not sure if I keep my calm. So I'll give you an overview on air quality management and air quality monitoring program, focusing on the ambient air quality monitoring. So my talk will include integrated air quality management, roles of monitoring in air quality management, and we talk about status of air quality monitoring program in global and in Asian countries. And the last and maybe the main focus is designing an ambient air quality monitoring program with NPC. So as you can see from here, when we talk about air pollution, as you can hear early today too, we talk about the link between the emission. So emission come from many sources, from cooking, from industry, from open burning, vehicle, and also natural sources like earthquake and volcano eruption. So emission is released into the ambient air, and then depend on meteorology. One day we have better air quality than other. So this is because meteorology determines dispersion and transformation pattern of air pollutants. And then it stops some ambient concentration, and depend on how high concentration, we see the effect on health, on crops and ecosystem, and effect on climate too. So the key pollutants to talk about, here we talk about major air pollutants. In the US, it's called criteria pollutants, so it's US EPA. And this is pollutant normally regulated using nation ambient air quality standards. You can see here particulate matters. So we have TSP, total suspended particles. We have PM10, we have PM2.5, normally we call it coarse particle, and now we have ultra-fine particles too. So, but it's not regulated yet, right? For the gases, we have sulfur dioxide, we have nitrogen dioxide, we have carbon monoxide, we have lead actually in particulate matters, so and ozone. So we also have other hazardous air pollutants, like we call it air toxic for US EPA, by US EPA definition. It includes volatile organic compounds like benzene, for example, semi-volatile organic compounds like carcinogenic compounds like PEHs, polysaccharide aromatic hydrocarbons, PCB, pesticide, heavy metals, dioxin, etc. And then we also recently hear more about short-lived climate pollutants. So these are actually harmful pollutants that having climate effect. And they are short-lived because they live in the atmosphere shorter than CO2 and shorter than climate. Average time is 30 years. So for global air pollution, let's look at the PM 2.5 concentration in 2019, so 2 years ago, right? This global map of population weighted annual average PM 2.5, and you can see here the darker color here over India, and you have here China, you have Southeast Asia, and you can look at the skin. So India, the level is only from 75 to less than 85. So this is the level, annual level, which is very high. WHO guideline is 10 micrograms per meter annual level. In China, the level is from 45 to 75 here, and Southeast Asia is about between 15 to 45 around. So in 2019, so the air pollution caused 6.7 million deaths, premature deaths we talk about, and among that, ambient PM2.5 caused 4.14 millions. Household pollution, mainly also PM2.5, caused 2.31 millions. Surface ozone is toxic ozone at breathing level here, caused almost more than 1/3 million here. So it ranked fourth in the list here. So in Asia, what is status of air pollution in Asia? So we have intensive emission sources. Not only too many sources, but also the source emission factor is very high because the control status is still quite limited. So we have traffic emission, residential combustion, biomass urban burning, agro residue urban burning, forest fire here. We have solid waste urban burning at home, in the landfills, and we have problem a lot with small and medium industry that emit a lot, very high emission factor on this small industry, but then the product at all. And we have seen very heavily relying on coal, and coal combustion is a big problem. So high level of air pollution observed, especially in urban area. And PM2.5, fine particle, is of most concern but we don't have systematic data or monitoring records. So it's lack of monitoring data. Surface ozone, it means toxic ozone at basin level here. It's increasing trends with very high level observed in suburban area where actually the cropland are. So that's where croplands is. So we have high ozone, the ozone impact on crops. For other pollutants, we can see the decreasing trend of CO, VOC, and SOx, but NOx appear to be increasing. So indoor air pollution is serious, and we also have transboundary pollution like acid rain, Asian brown clouds, Asian haze caused by forest fire, dust storm, etc. So we have serious impact on human health, crop and ecosystem, and also climate. But we do not have really comprehensive assessment yet because normally lack of the data. So this is a picture showing the UNEP report for solution report and show that in 2015 here, more than 92% of Asian Pacific people exposed to PM 2.5 annual level, more than WHO guideline, which is 10 micrograms per cubic meter. And then in that year, so ambient PM 2.5 caused 4.2 million deaths globally. And almost 60% of that occur in East and Southeast Asia. So now talking about for example here, so to show the PM 2.5 in Thailand. So Thailand is country have quite good data records, and you can see annual level, so almost for the 9 past year, and the level is only higher than WHO guideline, and the highest level can reach 45 here, annual average. And the level, the pollution, the source of pollution are quite intensive. And when we have stagnant air, it means when the atmosphere is not moving too much, okay? Not the wind is calm and the vertical mixing is limited, it is an episode. So this is show you example of the episode, which is very, very well known in Thailand and cause a lot of concern. The government also moved very fast in PM 2.5 control. So this is his episode in Bangkok in January 2019, and you can see up and down like this. So she is a pattern, so showing the regional effects, not only local source. And someday it reached 100 micrograms per cubic meter in PM for 24 hours average. And level is very unhealthy, like on 22nd January, this is published in the newspaper. So you can see very high level because it's more than 100, it's 165 here. So for the talking about PM, so it needs to give you some idea what is PM. So we have different parameters of particulate pollution. It depends on the size of particle. Look at, we have TSP, it called total suspended particles. That is particle actually normally lesser than 20 to 50 micron, depending on particle density. And this TSP is monitored by high volume sampler. And we have PM10, that everything that less than 0.10, it's called PM10. And PM 2.5 is everything is less than 2.5 micron, it's PM 2.5. We have ultrafine particles, so that include both. Normally, nowadays, include both of these range. The health effect of particle depends largely on its size, because larger particles normally cannot enter our respiratory system because our body have some defense mechanism. But the smaller particle can get deep in our lung. Okay. In alveoli, so we can see the particle with less than 2 microns, and very small particle, nanoparticle, can be found in our brain. So particle is quite complex. Particulate matter air quality is complex. Let's see how complex it is. We need to understand it in order to do the effective PM 2.5 air quality management. This is our concern in this project, right? Here in the ambient particles. So there are some particles emitted direct from directly from the sources like sea salt. So like dust, like fly ash, like black carbon. This is directly emitted from the sources and we call it primary particles. But a lot of particles actually form in the atmosphere. So for example, taking sulfur dioxide. So sulfur dioxide in the atmosphere goes through the gas phase photochemistry and turns into acid, sulfuric acid, and it neutralizes with ammonia emission to become ammonium sulfate particles. Similarly, we have ammonium nitrate particles, and we have volatile organic compounds that form organic particles. So we also have organic carbon emitted directly from the source. So meaning to reduce particles, we need to understand where it comes from. It's not only primary, but also a lot of that secondary. About half of the particulate matter measured in ambient air, so PM2.5, is actually secondary particles. So now talking about integrated air quality management framework. So normally, this is a framework, and then to do any air quality management work, we need to set some goal. So here the goal is ambient air quality standards. So for example, in Thailand, so 24 hours PM2.5 is 50 microgram per cubic meter. This is standard, and this is the goal. So we don't want the PM2.5 to exceed this level anywhere in the country. Once setting a goal, we will go and measure air quality to find whether it's above or below this level. And then we check whether it attained air quality standard or not, if it's meeting or not. And then if not, then we need to go for emission reduction. So at the same time, we also have the emission sources here. And then we can project the source, do the source emission inventory, and also with meteorological model, and we put in air quality model. And air quality model give you a better overview of air quality in your domain, in the city, for example. This is because the monitoring efficiency later we cannot do at many places because of cost, okay, because of resources. But then we actually supplement by air quality models in order to get better picture. So this is the blue color here are technical tools. So I understand that the first 4 days of this training focus on these 4 technical tools, right? And the source emission reduction is a control technology. So we cannot, this is actually technical tools. It should give us information. In order to reduce air pollution, we need to control the source. So here the example of the National Ambient Air Quality Standard and WHO guidelines for different countries. So here I got the number of Thailand and Vietnam. So these 2 countries actually still regulate test speed. In Vietnam, it's still 1 hour test speed regulated. So in the US, so they have 24 hours of PM2.5 certified microgram per cubic meter. And they have 2 annual standards here. One is for primary standard. It means for protecting our human health. And then 15 is for secondary, it's for protecting our welfare. And then we have Indian for the second class standard, and then WHO guidelines. So you can see the different countries have different air quality standards. It means they have different goals in order to achieve. And one WHO value are quite different because it's for health, protecting human health. And then for this WHO air quality guidelines, this is current level, but soon perhaps they also have to revise that and to make it more stringent, as long as we have more evidence for that. So now talking about air quality monitoring. So why we need to do monitoring? So we cannot control what we cannot measure. If we cannot measure the thing, we cannot control because we don't know. So the monitoring helps us to identify problems, like whether it's high or low, or what are the pollutants in your city, and then we identify problems by monitoring, by emission inventory, by source and impact assessment, and then the second step we go for formulate policy. And with that, we need to use modeling tools, scenario evaluation, cost-benefit analysis, and then we control situation. So air quality management requires systematic and reliable information on status and trend of pollution. And the goal of monitoring is to generate data of required quality for use to protect human health and welfare. Data is the goal of monitoring. And then the QA/QC is very, very important because the data of poor quality or unknown quality is less useful than no data. So if we have the wrong situation, wrong information, if level is too high, but then we actually our monitoring results show is very low. So then we do not do any action. So it resulting a lot of adverse effects. And opposite, if our level is not high, but our results are showing very high, so in that case, so the control action will be taken. Actually, it will be good, but anyway, we may have other priority to do for the environmental pollution or environmental management. So the development in the air quality monitoring techniques. So this is show the chart here. So in 1960, so in the US first, they started with manual fixed station. And the key pollutant to measure is TSV, NOx, and SOx, and mainly outdoor. And this is for regulatory purpose. And then for research, later on, they also focus on fine particle and then verify particle here. And then later on, they start with mobile station, the fixed and this mobile. And since the 1990s something, so we have automatic station, so and automatic gas and PM monitoring. And here we also start not only outdoor, but focus is more on indoor. And there are open paths like DOS system. And right now we talk a lot about wireless sensor that you can see talk today too. Satellite imagery, use satellite product. And then wireless sensor is good because we can capture it and put in Internet of Things. Right? So the categories of air quality monitoring programs. So first we talk about ambient air monitoring. And we have source emission monitoring, we have mobile source, and we have stationary source. Mobile, it means vehicles, and stationary like industry, power plant, stacks. The personal exposure monitoring, so nowadays local sensor used for a lot for that. Okay, people carry the monitor with them on the way and then showing how much they are exposed per day and in different location in their routine activity work. So indoor air quality, like workplace monitoring, residential indoor air quality in office, and vehicle in car that measure in closed environment. Now, talking about status of air quality monitoring. So this is showing you some example of global and regional monitoring network, and mainly for research purpose. So we have WAT, okay? So global atmospheric WAT. So this is, you can access it online, and you can see information there. And now it's in the US mainly, they actually have the air quality index reported. And they also have international data measured by US Embassy and Consulate. It's quite reliable data. So we have, in the region, we have ENET, so Acid Deposition Monitoring Network. In East Asia, it is sponsored by JICA. And lately, they also monitor concentration of PM2.5 and gaseous pollutant. But of course, the purpose is acid deposition. So they have more acid deposition data than air quality data. So in the world, how many countries have the data on air quality? So this is in a survey in actually open source, open air quality data in July last year. It shows that over 212 countries, okay, 49% of these countries have air quality data in some capacity, in some form. Remaining 51% of countries represent a total population of 1.4 billion people have no data. So in the Asian and Pacific, by the UNEP trackers, it's showing that 26 out of 41 countries have official air quality monitoring stations, and where they monitor normally PM2.5, PM10, ozone, now NO2, SO2, and CO. And about 30 countries have real-time data, but not yet fully shared online. And this is data sharing, right? So now, yeah, increasing number of human citizen and civil society using local sensors in order to fill in the data gaps. Now we talk about designing ambient air quality monitoring program. So this is actually the focus of my talk today, really. So we have two types of regulatory two types of ambient air quality monitoring network. One is regulatory. So regulatory is run by government agency, and we in this network, the key pollutant to monitor is criteria pollutants. It means the pollutant regulated by standards, and the purpose to check compliance with the nation ambient air quality standards. So this monitoring should be conducted according to the nation ambient air quality standard requirement, like the methods, what kind of equipment, what methods, what is the averaging time, how frequent we need to monitor, and what kind of monitors. Normally we use the regulatory or reference monitors, like federal reference standard, federal reference equivalent methods. So other monitoring network available is a lot. It's called participatory by citizen and by civil society. So this network, as you can see, mainly use local sensor, wireless network to complement regulatory data. So for personal exposure, the participatory is like hands-free monitoring. So how much we are exposed to different pollutants during a day of our life, for example. And this local sensor or monitors, as you can see later by our colleagues who presented today, they still have a lot of problems. So we need to, if the citizens are given a sensor, we need to guideline and support them to collect the data effectively, to analyze the data, interpret the data, and communicate the data properly. Now, what are the challenges to obtain representative monitoring data? Why a lot of challenges? The first thing to think of or to consider is large variation of in ambient air quality. First, ambient air quality is a dynamic and complex environmental phenomenon, and it has very large temporal variation like hourly, daily, monthly, even every minute, seasonally, and it has also large spatial variation on different scales. We talk about local and neighborhood, urban, regional, hemispheric, and global scales. Why the air quality varies a lot? So first, we see the change in source emission rates. Say during a day, early in the morning, when we have traffic rush hour, then we have high level of CO, PM, NOx, for example. And late at night, the level is dropped because the source is limited. So for location, it depends. The urban air quality is different from the rural air quality because the sources are different. And secondly, we talk about changes in the meteorological condition. So it causes mainly temporal variation, okay? Change during months or during daytime. So when we have good mixing condition, we may have better air quality. So evening, so when we have stagnant air because of inversion, so we have worse air quality. Okay, so it's very challenging to adequately characterize air quality because it varies a lot. So in designing an air quality monitoring network, so we only talk about PAQC. So first, we need to define monitoring objectives. Okay? So that's based on the local and nation requirement, nation ambient air quality standards, or international agreement, or other purpose like for research, for historic assessment. So it means you define how the intended use of the data. And then we go for the designing the network. We decide how many sites, where the site should be located, what kind of instrument need to deploy, how to operate the site, support the site, and calibrate the equipment. And finally, you get the data. We need to talk about data management and review and reuse it, and then use of the data. And then use of data, of course, we need to disseminate the results, publicizing the information. And the network needs to have systematic review, periodic review all this, okay? And all these actually defined, dictated by data quality objectives, which I will talk later. And number of the sites, it depends on equipment, etc. Depends a lot of the resources available, like how much budget you have, skill level you have, and time resources. Now, when we do designing an air quality monitoring program, the question to ask, a question to answer, why do we measure? That is objective. What data quality and quantity we want to have? That is data quality objectives. What should we measure? This is indicator. What pollutants we measure? How can we measure? The which method, which equipment? How do we handle and store data? So this is data management. And how do we want to present the results and result presentation and reporting? So this is a question we need to answer when we do designing an air quality monitoring program. So this is the steps that we need to perform in order to ensure data quality. First, we need to set clearly the monitoring objective. For example, if the objective is to find a trend, or a trend during like 10 years, so of course monitoring needs to do for the 10 years, okay? And if we want to find a hotspot, then we actually need many monitoring locations in order to find where it's high, where it's low, okay? And then with the monitoring objective, so it define or dictate also data quality objective. So we determine the data quality and quantity that we need in order to fulfill the monitoring objective. And then we go for equipment selection. So the results, all these equipment need to select in a way that it produces the data that meeting the data quality objective. And then we do the size selection. So size must be representative to meet the monitoring objective. So that's why in ambient air quality monitoring, if we want to see the air quality in different places in your city, then we need to design properly in order to get the data from different typical air bubble or zone of the city. So for the monitoring objectives, so why do we measure? Okay, so here the basic objective. The first one is timely report it to public, timely public reporting. So it mainly assess short-term pollution level. Like if you go to air for Thai, you can see hourly level there. Okay, I will show it later for 24 hours, and to develop an air quality index or other tools for communication. Normally for public, we use air quality index, and for forecasting, activate the emission control procedures. And second basic objective is to do for compliance and planning. So compliance check, first we check with the ambient air quality standard, whether it's higher or lower, to see it exceeds or in compliance or violates the standard. We also do the observe pollution trend for long term, different months, different seasons, and formulate pollution control strategy and evaluate effectiveness of this strategy. For example, in a city, you ban crop residue or coal burning for that year. So you need to do monitoring in order to see whether it should really have some good effect on air quality. We do it to support nation and international agreements and initiatives, and then provide data for evaluation of air pollution impact and for urban and transport planning. So this is the sub-objective of that. For research can be anything. So can assess impact to different groups of population, ecosystem, and assets. Okay? Develop and validate management tools like model. Okay? We get the data from monitoring activity in order to compare with modeling results to do the model performance evaluation. To discover new pollutants, develop and test analytical instruments, and of course do source enforcement studies by receptor modeling, which is our talk today too. So data quality objective, it means how good data one for the intended use. So data quality objective process define the most appropriate type of data to collect and the most appropriate condition from which to collect the data, and specify tolerable limits on decision errors. For example, we say accuracy is 15%, precision 10%, repeated measurement should not be differ from each other more than 10%. Time coverage, like more than, if we have automatic station, we say it should have more than 80% of hourly measurement in order to use for compilation of annual average, for example. So this is, we have QA during the planning, we have QA QC during implementation, and we have QA in assessment. So QA is, by definition, you can understand it like everything someone else do to check if you perform the QC measure. And QC is whatever you do, like calibration, like zero and span check, so that you do. And QA is someone else check and plan for you. And for assessment, validation of data, also QA, someone audited, someone have a look at that. So air quality indicator is similar to what I mentioned in the pollutants. Okay? We have criteria pollutants monitored by regulatory networks, PMs and lead, gases, air toxic. Like in Thailand, they have also VOC standard. It means they also monitor VOC in the ambient. For the other place, actually, if you want to start, so it could have some priority pollutants. For example, if we monitor the impact from industry, and that industry use cement production, then we will look at PSP, PM10, PM2.5. If we have the coal-fired power plant, we look more at SO2, fly ash, for example, and NOx. So for the urban air quality, as I mentioned, it's similar to criteria pollutant here. The regional contribution, that pollutant have the long-range transport potential, like ozone and ozone precursor, particulate matters, and say also the precursor like NOx and SOx, and then we also have mercury that also transport cross boundary. The last scales to domain, we talk about Southeast Asian haze, okay, and Asian dust. When we do monitoring, so we remember that we only need to have the meteorological parameters because it's required for data processing and data analysis later. For siting here, siting it means where do we measure? It depends on monitoring objective. If we want to do population-oriented sites, it means we want to have exposure assessment. So we should measure where people live, where people play, and spend their time. If we want to do the compliance side, so then we need to select the representative location in the city or in your area and compare with the standard. It means include low, high, and very high level, for example. A special purpose monitor is to assess natural or man-made causes of excessive concentration. Like in Thailand, they have the Memoir power plant where they have more monitors. Okay? And in Chiang Mai also have more monitor in northern part because they have biomass urban burning. So transport side is not traffic side, right? Transport side here means the transport of pollutants, flow of that. So we have the remote side, that is where we have no impact, and then we have upwind side, and then we have downwind side of the city. So that is transport side to design the transportation of pollution, right? Background side is very far away from any human activity and want to see what is background level in your country or very far away from the urban area. So when we do the siting, the key consideration here is distribution of emission sources. Whether it's the source, you need to consider both inside domain and outside domain. If we have upwind of the urban area of concern, have big outland, and even if not in your domain, but you need to look at that because it will help the pollution transport from that stack and affecting the concentration in your domain. So we need to check the terrain and area of the domain, of course. We need to have to see population and population density for exposures assessment. For distribution pattern, we need to look at windrows because we want to see upwind and downwind, for example. So in Asia, we normally have dry and wet season and the wind change, right? Opposite wind. So that's why upwind side in one season could be downwind side in another season. So that is, we have two. And when do the siting consider any available data? Any available measurement data, emission inventory, okay? Modeling design satellite in order to determine spatial distribution of pollutants. So when we capture the representative location for the data. So general consideration when we check location of monitors. So you need to provide the exposure of monitor. It means minimize the nearby patterns, like not locate the station near big building or under the trees, because then would not have the good exposure for the monitors. So minimize nearby emitters. Of course, if we want to do ambient monitoring, we don't want to place it next to a source because we want to have ambient air quality data. Maximize co-located measurement. So if the sites or nearby have meteorological station, would be very good because it would be beneficial to get the data for the results processing and analysis. Ensure long-term site commitment. So in developing country, the planning, urban air quality planning, and then construction is going on a lot, and it changes a lot. So it's better to find a site that you can actually put it for long term. Otherwise, after a couple of years, the new building actually already there in the place, and then it blocks your station, and station is very expensive, as you can see later. For other things, it's like micro issues like proper siting. When we have already the site may be very good. And one time I came and checked my project in other country, and I found that they actually locate the monitor next to the exhaust of air conditioning system of a hospital. So that is not representative. Even the site is very good, but the problem is not good. So I need to move it away from the exhaust. So this is an example of siting in Asian Center for Environmental Management of Vietnam by Clean Air Asia Project. Actually, first, we want to check the impact of urban burning of restaurant in Hanoi on ambient air quality. So first, we look at the rice plantation area in Hanoi. We also check the windows of different months. And finally, we come with the sites here. Okay? And then we conduct the monitoring for 1 month during the burning season, and after that, in order to compare. This is the station Hanoi during that period. So how many sites? What we want many sites. Many sites would be better to have more data density. However, we need to consider the cost and the resources and the data quality objectives. If we want to do the local sensor, the purpose is to do the hotspot analysis. So we can calibrate local sensor and put in many places and in the city and see where it's high. So high concentration, it means the hotspot. But then if we want to do a regulatory network, so the cost of the station is very, very high. Right? If you want to see how many sites, I'm not going to deep inside that, but I give you some reference here. Okay? For EU, the number of fixed sites based on the ambient pollution levels for PM and for other gases, and the population that exposed to that in that domain. Similarly, US EPA also based on air pollution level and exposed population, and they have separate guidelines for specific pollutant, like separately for PM2.5, for example. But China considers the domain area and population. Consider both domain area and then population, and whichever gives larger number of sites, so select. So this is the technical regulation for site selection in China. You can also check the reference. Resources, how expensive it is. Now we are setting up a standard and reference station. We need to consider center with electricity, analyzers, equipment, calibration system, data router, storage and transmission, consumables like tubing, standard gas, air conditioning system. So budget, it depends very much on the location, land and labor costs, electricity, internet, etc. The target life of equipment, normally we want it to help from 8 to 10 years last. Longer the better, right? The estimated resource needed instruments is from 10K to 100K for instruments. Okay? The startup cost is around 200 to 300K per station, and operation from 10,000 to 80,000 US dollar per station annually. So every month is around 1,000 US dollar, but depend on if the station is inside city or in remote area. Remote area is more expensive for the operation cost. So talking about the methods. Okay. So how should we measure? There are two main considerations. How often do we need to measure and what methods? So This is on depend on the monitoring objective and data quality objectives. Now, for the sampling frequency, see it here, it's dictated by the National Ambient Air Quality Standards. This is example: carbon monoxide, nitrogen dioxide, ozone, sulfur dioxide, PMX, and lead. Okay. So as you can see, unit for the gases, we can use 2 units. Both of them, and they are convertible. So you can convert one to another. So carbon monoxide level is very high. So it measures milligram per cubic meter or part per million. So the gases is microgram per cubic meter or part per million. And for particles, so we need to use microgram per cubic meter. When we do the microgram per cubic meter, so cubic meter is the volume of air changed with temperature and pressure. So when we report this unit, okay, mass divided by volume, so we need to indicate temperature and pressure of measurement. If we report the volume by volume, we do not need to report pressure. So this depends on standard set by your country. But the carbon monoxide and nitrogen dioxide on this gas is measured by automatic analyzer, so it gives you hourly concentration, hourly integrated concentration. Even we can actually program it to be more often. So for PMX, hourly, if we measure it by automatic analyzers, but if we do the manual sampling, it's daily, 3 hours. Okay. For lab, the measurement is every 6 days, according to US EPA. So you may ask, why 6 days? Why not 7 days? Okay. I asked you that question, why 6 days, not 7 days, right? And we can answer it later. Now, everything time is very important for air quality data. So for example, here, the variation of carbon monoxide at roadside. You can see at rush hour, concentration is very high. During midday, when we have less traffic on the road, level is lower. And evening rush hour, high again. Okay? So this is depend on the sources. Okay? So if we have standard for hourly concentration, and we come early in the morning, so we come late, we come at 10 o'clock, and we measure level somewhere here, and we compare with standard, it's not correct, because CO standard is set for maximum hourly concentration of the day, meaning that we need to monitor every hour and get the maximum compared with standard. So everything time is very important for air quality, not only because of variation in of air of the level in the ambient air, but also for the exposure assessment, because the time is very important variation for exposure. Exposure is function of concentration and time. Okay, so that is very important. So for monitoring techniques, so I don't know how much time I have. Okay. So monitoring techniques, we have manual sampling, so intermittent sampling and lab analysis. We have graph sampling, integrated sampling, active sampling, passive sampling. The active, it means we use a pump, and passive is we don't need a pump. We need a trap for the chemical trap that trap the pollutant of interest. We have continuous and semi-continuous automatic real-time analyzers. We have other advanced techniques, in situ measurement like DOS, remote sensing, satellite image for large-scale monitoring, wireless and local sensor, rapidly for data publicizing. This is example of PM monitoring. So equipment in monitoring particulate matters, you can measure mass directly. This is by sampling. We use a filter with a millivolt, right? So while we have a filter, and then we collect particles over 24 hours, we wait the filter before and after the sampling, and we know how much volume of air passed through, and then we calculate concentration. So this is for TSP, this is DICOS for both PM10 and PM2.5 and cost fraction, the cyclone, and cascade impactor for different size range. So nowadays we monitor a lot because of online monitoring. So we measure the optical property. It's not the mass, but the surrogate mass. Okay. So measuring absorption like atherometer, we measure black carbon. Scattering nephelometer, we measure ozone sun, beta attenuation BAM. Okay. So particle numbers. Nowadays the particle gets smaller and smaller. Ultrafine particles. It's very difficult and almost not possible to weight. So we count. So different equipment are used for counting particles, like RIM, like particle plus sensors. So we have at IIT, we particle counters. So this is an example of beta ray attenuation monitors. So we have inlets, whether it's PM10 or PM255, depend on what you monitor here. The particle is to take it probing inside here, and here we have a roller, we have clean filter, we have use filter. So it programs that every hour the filter advance. So when it's advanced, so then we have a low beta radiation pass through the filter layers, and then we actually have the detector, and that is actually the mass of PM inversely proportional to beta ray, that energy penetrating radiation that we can reach a detector. So normally the manufacturer won't recalibrate it to get the mass concentration directly. So this is continuous active analyzer of gases. So you have very high resolution data, hourly or less. So typical for all gases and can stream data to internet rolling time. The disadvantages are they are expensive. Okay, so they need regular service and maintenance, and they need power from the grid to operate. Okay. And we need housing and shelter with air conditioning system. So the summary of the measurement methods here. For gases, we can have passive sampler, we have active sampler, we have automatic analyzer, we can have remote sensor, gas and satellite. For PMX, we have active sampler, automatic analyzer, and AOD, ozone optical depth. And left, we need active EHP sampler. More and more wireless sensor and satellite for use of satellite products, so that is increasing. And so use of wireless sensor and satellite product for measurement and atmospheric composition. So this is example of a station in the US. So you can see meteorological data, the particulate inlet for gases about the station. So in terms of data quality, data management, right? So I would not go very high because it needs more time actually. The goal of data management is to have the data validated and managed after it is obtained. To make sure that data stored is of good quality. The key activity here we need to check and validate and code and store the data and analyze the data and present the results properly. The poor data quality means measurement of errors or data floating too many data points to handle manually. These are key challenges for data management. The key accuracy are needed in every step, also in the data quality management step, in order to ensure that the good data are obtained in the monitoring network. So this is data management. So start with the data system task first with monitors. To capture the data, transfer the data in the database, okay, and the data accuracy, and then we also have supporting information for emission inventory modeling, and then data analysis, and then present the data, publicizing the data, use the data for decision making. So for data management, so the key indicator of data quality is accuracy, precision. Accuracy is how close the measurement with true value. Precision is how when the measurement repeated, if we actually perform the same sample. Representativeness, it will represent the location or the time of the monitoring of the measurement, right? Station coverage, one station per city, not enough. So how many stations? And we already mentioned about that, right? Temporal completeness, if we do annual, so 1 year, we have hourly data. So normally it requires more than 80% of the hourly data in order to use that data for annual average computation. Detectability, this is depend on the equipment. The equipment should be sensitive in order to detect the low level. Comparability here, which is actually very important for developing countries. This is because the data we may generate by different techniques, different equipment. So we need to compare that and allocate the equipment in order to have the single data set, because we cannot, the two different monitoring methods may not produce the data that's comparable. So for the data presentation and reporting, so remember, so we may have different level of detail for different audience. For professionals, like for researchers, we normally need easy access to the raw data so that we can analyze it, and then we actually, in order to have the objective of our research. Okay? So for policymakers, we need a very brief, very concise information and present the conclusion in order to convey the message directly, whether the level is higher than standard, lower, or increasing or reducing. Okay? For the public, they need information on the general state of air quality. Normally, we use the air quality index because we need to advise them how to avoid exposure. So air quality index, so we do not need to present the microgram per cubic meter or part per million, part per billion, but we use color. So this is the example of RRC.AP. And I understand many of your country also using similar color scale. And then here you have also caution statement for different people, how to avoid exposure, and he also present the range. And when we present this range as researcher, I don't like it because it lost a lot of information. Okay, but then when for public, it's good because it's colorful scale. So this is the ambient air quality monitoring network in Thailand. As I mentioned, Thailand have quite advanced monitoring network. So long ago, so they already have started in 1994, if I got it correctly. So already started the network and it operated very nicely since then, generate a lot of data and very easy to get access. Right now, the data, air quality data of Thailand is online. You can go to Air for Thai, you can search and see it online, right? The total number of stations operated by PCD, Pollution Control Department of Thailand, is about 70. And during the last 3 years, the number of monitor of PM2.5 increased very fast because of interest on PM2.5 right now. And they have two types of station, general station that is located away from the road, 100 to 800 meters from the main road, right? Main road, not small road. Yeah. Curbside and roadside, it located from 3 to 5 meters from traffic lanes. This training is online. That's why you don't have a chance to visit a station in Thailand. Hope that next training you will have a chance. So this is references. Thank you. Please post your question and on the chat box, question and answer.
Thank you.
Because we started
Thank you, Professor Kim.
Thank you.
Thank you, Professor Kim, for your nice presentation. Actually, we are behind the schedule of 10 minutes, so we cannot take questions, but I will ask one question from participants, which he asked, which guideline of air quality monitoring is good for developing countries?
For again,
Which
is it
guideline
science?
of air quality monitoring is good for developing countries?
Wow, a lot. It depends on which developing countries, what level of development, and whether you have already some station or no station yet. So that is. But let's first check with the Clean Air Asian Clean Air Frameworks, right? Guidelines that I posted here. Okay, look at this. Clean Air Guidance Framework, Area 1 monitoring that I believe Dr. Verma already posted it online for you. Huh? So
Yes,
this is
we have
very much
posted.
for developing countries.
Yeah.
Yeah. One maybe also China also look good. So, but they very big countries. So you may want to see some countries that small, like New Zealand, also have very good. But Clean Air Asia guidance framework, I would recommend first to start with. But US EPA have very comprehensive guidelines for heavy pollutants to check with too. Anything else?
Okay. We do not have time to for more
I can
questions.
look at the website and I can check through.
Yeah, if any participants have questions, please either put on the chat box or write to me. I will pass your questions to Professor Kim for answer, maybe later. So now we are very 10 to 11 minutes behind the schedule. So the next presentation of this module, the air quality monitoring, is from Professor Satchidanand Tripathi from the Indian Institute of Technology, Kanpur. Professor Tripathi, the presentation is on air quality monitoring using the low-cost sensor. Professor Tripathi is a senior professor and head of the Department of Civil Engineering at the IIT Kanpur. He holds the Arjun Dev Juneja Chair in Civil Engineering. He is the recipient of Shanti Swarup Bhatnagar Award and the J.C. Bose National Fellowship. He is an elected fellow of the Indian National Science Academy, Indian National Academy of Engineering, National Academy of Science. He was a senior fellow at the NASA Goddard Space Flight Center. Professor Tripathi is also on the editorial board of several journals such as Environmental Science and Technology, Letter, Journal of Aerosol Science and Environmental Science, and other journals. He made an impactful contribution to address challenges of air pollution and climate change. He has built an indigenous low-cost sensor-based network for nationwide urban air quality monitoring and real-time source apportionment. He is also a coordinator of the National Knowledge Network of the National Clean Air Mission, formed under the National Clean Air Program of India. Professor Tripathi, the floor is yours.
Thank you, Dr. Verma. I hope you and other participants can hear me well.
Yeah, we can hear you.
Thank you, and very good afternoon and morning, depending on where you are joining from. So let me share my slide. So Verma, can you see my slide?
Yeah, we can see. Make it full screen.
How about that now?
Yes. Yeah, you are done. Thank you.
Okay. So next 45 minutes or 50. First of all, I thank Dr. Verma to have me here. It's really a very, very timely workshop. And what I understand that we have participants from across probably Asia or maybe beyond. So it will be a great opportunity given that air pollution has assumed, such a problem of such a scale and menace. So definitely, just before me, speaker was talking about, I believe, air quality monitoring using the equivalent reference grade monitors. And I'm just going to add to that how we can augment or supplement monitoring, air quality monitoring using sensors. So I work at, as Burma said, at Civil Engineering Department of IIT Kanpur. So these are the following things which I'm going to mainly cover in this talk, is that what opportunities we have in this domain, that is using sensors for air quality monitoring. And then I will also show a couple of examples from different parts of the world, including India and other places, that gradually governments are showing more kind of, you can say, affinity towards using sensors and sensor-based monitoring. And the reasons behind that would become clear as we go along. I would also talk about some end-to-end air quality monitoring solutions, that what other aspects you have to bring in if you want to have the pollutants sensed, and then from there to actual numbers or air quality index that you want to see on your device or through a variety of ways. And then I'll also show that one interesting work we have just done with one of the state pollution control boards in the country, which is Maharashtra, where Mumbai is, that they wanted us to use their network, that is government monitors, with an aim to understand the accuracy of these sensors. So I'll show some results from there. I will also give some idea about how is the cost of sensor per se, or the overall end-to-end solution vis-a-vis that equivalent reference grade monitors. And then again, I will give some more applications for society and citizen-centric science, whatever you may like to say, and then summary. So this is what is the current overall is what you see, that the market size is basically that what on the left you have the PM sensors, where it currently has a market size of $2.5 billion. And in India itself, it's just about $200 million. So you can see that, and this is the market size, which of course is growing very fast. And the market for gas sensors are not so far behind. It is about $1.7 billion. And then certainly Asia is a place where you need a lot of these sensors for monitoring, mainly hyper local monitoring. And what do we mean by that, we'll see. And if you look at the end-to-end solution, that is basically from sensing to getting the data in the form which is useful for variety of purposes, to regulator, to citizen, or to schools and hospitals, that of course that market is even larger. So it's already, it's almost going to reach to about $1 billion or $1 billion in India. If you try to compare this with, let's say, some of the other technologies that there are some interest also that where people want to use satellite retrieved optical depth, and they use certain procedure to convert optical depth to PM 2.5. But then, this slide just gives us some idea that what are the pros and cons of satellite-based measurements. So just to give the things in perspective. Of course, I'm sure you have got a lot of idea from the previous speaker's talk that what are the strength of equivalent or reference equivalent grade monitoring monitors or technology. And here I'm giving another interconclusion. So what you see that there are some issues with satellite-based monitoring. One is that you try to retrieve, because the basic measurement using satellite is done using the outgoing radiation, that is the reflectance, and then you use couple of models, atmospheric models, to derive basically the attenuation that happens because of particulate matter in the atmosphere, and that is also in the total column of atmosphere, which generally you take as about 15 to 20 kilometers. Now, certainly some errors creep into this retrieved quantity, that is optical depth, because and that is basically an integration of this entire attenuation across the atmospheric column. And there are two major issues which one finds there. That one is that, of course, the type of surface, and second, of course, how do you exclude cloud or depending on type of aerosols. And that's why people have shown that you could have an error of about 25 to 30% only in optical depth retrieval. And you see, optical depth results from integration of PM 2.5 across the column. So that requires that in order to have the PM which you breathe, that would require the vertical profile of PM 2.5 and its chemical composition and size distribution. And most of these, are hardly available for many parts of the world. So therefore, some additional error also creeps into that. So if you add these two errors, of course, the total error goes up to 30 or 40 or 50%. So one is that because you have two, step estimation, right? So you are not doing any direct measurement. That's one problem. And then there are, of course, also the data coverage and data frequency issues, because satellite can only cover a part of the world at a given time, and it only crosses a particular spot once a day or twice a day. So if you're looking at a maybe year-long data set, of course, or a multi-year decadal trend, it can serve the purpose. But if you are looking at probably a diurnal variation at a particular spot, then of course, these satellite, derived PM 2.5 is not going to be of much use. And finally, as you know that, because you need to remove cloud also, that cloud related interactions, which also contributes to reflectance, that creates a problem during fog or monsoon, or whenever you have overcast or a cloud over the period where you are interested in getting the PM 2.5 measurements. So these are, of course, there are several these issues one has to keep in mind when you are trying to do the measurements using satellite. Now, if you look currently where the state of art is, so this is just a slide I could get from a conference where some authors from China, they presented it. And what you see that they have really developed a very state-of-art system. So here on the very right, what you see that the network size, which shows all the dots, and the bigger dots are basically the government monitors. So what you see from here is that across China, estimate is that they have about some tens of thousands of sensors. Only Beijing alone has about 1,000 or so sensors. And they have certain processes in place where they can do calibration on the go. They have also mobile laboratories through they do the calibration, and all that data goes to the main server, which is shown here. And they also apply several servers online. That is, dynamic calibration they apply on the server side. And then, of course, this data they are already using for a variety of purposes, right? They are using it for basically assimilating in weather forecast modeling. They're also doing it for other kind of forecast, and as well as, of course, for air quality monitoring data. And then it also goes into basically air quality forecast systems. And finally, what the way they are doing it, I believe it is already operational, because I didn't get much information on this, but I believe that their goal is that all this information can be live broadcast to the people at large in the country through television and through various portals, newspapers, etc. That so that people are totally aware of the air quality in their neighborhood. That's next to where they stay, what they are breathing. One is able to get that information. Now, here is another interesting, you can say, a paper that provided a framework for India. So as Dr. Verma pointed out, that we are also part of this National Clean Air Program, which Government of India launched in 2019 January. And certainly, India has a very sparse, as of now, monitoring network. So as of today, I believe we have less than 300 continuous air quality monitoring stations in the country, and there might be another few hundreds which are manual monitoring stations. So basically, the required monitoring stations, which runs maybe of the tune of few thousand, and with few hundred, you have a large gap. So given that, this is a kind of a framework which this paper gives you, that going from a global level where you can use either the chemical transport modeled outcome to give you the air quality forecast at the level of few hundred kilometers, so maybe at an air basin level, and then you can use it to downscale the data from the regional model that can provide you data at the city scale, and from city scale to local scale, one could use a hybrid approach where you have a combination of these continuous air quality monitoring stations, as was discussed before, that which includes the PAM and all kind of gas analyzers at selected strategic locations, and supplemented by a very dense sensor monitoring network. And that's the idea where probably we hope that the future monitoring would move in India and maybe in other places. In fact, already what you see that this is a snap taken from US EPA website. So this is what they are currently doing, that they have about 10,000 plus or so sensors across the country. And most of them, I think, are purple air sensors. And as you know that US, only EPA has about 850 to 900 continuous air quality monitoring stations across the country. And there might be additional these stations maintained and run by other state agencies, other state and district air districts and other agencies. Now they are able to use all this data and to make a synthetic product. And this information, in fact, they are already using to give information about smoke tracking, particularly in this case, that because you know that some part of US is always very well impacted by some large scale forest fires, and that quickly and severely deteriorates the air quality in that region. So in those areas, certainly citizens and residents are very much keen to know what's happening to air quality. So one use what they are doing is this. And but in addition to that, I believe that many of this data is also available to get an information of air quality at the neighborhood level. This is another very interesting thing, as some of you might be knowing, is about a sensor-based network which City of London has commissioned about a year or more before. And what you see here, there are two plots. Left is the bubbles show the concentration of NO2 in different parts of London, where basically a stationary network has been used. So sensors were not moved around. And that gives you quite a good idea about, at a scale of probably few hundred meters, that how different sources, and in this case, possibly their interest was more to understand how the vehicular emissions are contributing to the NOx concentration, or different, very, very fast fluctuations in NOx next to road or other places. And on the right, they have done the same thing, but by placing the sensors on a mobile laboratory. So that's why what you see that you have very clear profile of NOx, and which is shown in the different colors. So different colors gives basically that what is the concentration. So, if you go to the very light color, is less than 10, and then if you go dark, it's more than 200. So you can see that you can have a very, very good idea about what is actually, what the air you are breathing, what's the amount of PM and different kind of gases which is present there. And definitely it makes you more informed, and then it gives more information to the regulatory agencies, to the government, and they can make very, very informed policy decisions based on this. So let me now turn to a couple of work which we have done last several years. One, what it shows is that we tried to do the calibration of PM 2.5 sensors. So all these results shown here are basically using plant tower sensors. And what you see that basically we have these 4 results, and these are for 2 different seasons and doing 2 different kind of averaging. Okay, and these results are from India. So on the left, what you see, the extreme left, you have monsoon for a 1-hour average data, and the next one is monsoon 24-hour average data, and statistical parameters are given below: the intercept, the slope, and R square. On the x-axis, you have the BAM measured PM 2.5. On the y-axis, you have plant tower measured PM 2.5. And they were, of course, co-located, and all that care was taken. So what you notice here, that certainly in monsoon, when the concentration was low, some of you know that definitely we are not getting very, very high R square. This is reasonably good. It's going up to about 0.8. But when post-monsoon, that is in India, it's from November to October, November, and maybe part of December, you can say, that exactly in same format, 2 figures, you see post-monsoon 1 hour, post-monsoon 24-hour, and then you notice that R square has improved. It has gone up to 0.92 or even more, and we also saw that error reduced significantly. So some of these values I would show in another table where I have summarized them, and we found that generally a linear fit is good enough as a curve, calibration curve, which you want to basically get an idea about how accurate these sensors are compared to the BAM monitors, right? And very similar results were also found when these co-located experiments were conducted in US. Certainly because the concentration in US was generally much, much lower than what was done in Kanpur. So the R square, of course, was not as high as what is seen in this slide. But one interesting thing was also noticed there, that if you do a relative humidity correction, so if in addition to BAM, if you have an instrument which gives you particulate matter 2.5 as a function of relative humidity, where you are able to compute the growth of the particle, right? So from that, you can get a very accurate estimate of the PM, because many times, in very high relative humidity, you can have an artifact in particulate matter measurements, and you might be measuring a droplet, that is a particle which has large amount of water in that. So in that case, you need to do a correction to get actual PM part of it. And we found that in US, if you do that correction, in fact, again, you can get a very high R square. This was a follow-up work which was done basically using a network which was operated in Delhi, a sensor network that was operated in Delhi for about 1 year. And the idea which was pursued in this particular work was to develop a machine learning based approach that can avoid the need for having a co-location, because one has to understand that in real life scenario, you cannot have always the luxury to bring the sensors and co-deploy with a BAM monitor, because that certainly would require many other logistics, and including, of course, you would have a issue of paucity of data from where you move the sensor, unless you have a substitute sensor. So idea basically was that if you have interspersed government monitors, that is, if you have 30, you see that there are different dots, and those are shown that there are sensors, and then there are government monitors, right? So you can really develop or use some kind of these very well used technique in the machine learning, in this case, of course, Gaussian process regression, which would allow you to iterate the value at a particular sensor till it matches to the neighbor government monitor. So if they two are matching within a precision, then certainly you could say that, well, but it is not next to the monitor. Remember that. It is in the neighborhood of the sensor. Monitor is somewhere close by. So that way you could apply this entire iterative procedure over each and every sensor, and where you have fitted a distribution, across all the monitors and the sensors. An idea is that one by one, in a very dynamic way, you can understand and calibrate every node of the sensors network. So certainly these are some of the ways you can apply calibration in the field. Of course, there is another approach, as you know, and many people are using, where you certainly move a BAM on a mobile platform, and then you bring it, co-locate with the sensor where you, or which wants or which needs to be recalibrated. So that's one way. But you know that in this case, you will have to basically bring the mobile laboratory and you have to go from one sensor to another. So of course, there are pros and cons of both methods. This is another just a follow-up work which we did again in Delhi. And the idea here was to again look at the precision and accuracy of PM10 sensors, right? Because we know that many places still PM10 is a part of National Air Quality Standard, or is mandated under that, and where PM10 is also a criteria pollutant. Certainly, it is one of the criteria pollutants in India. So here we used again plant tower PM10 sensor, and we tried to look into its accuracy by placing it next to some of these reference grade PM measuring instruments. In this case, we have not used BAM because we were actually not running BAM that time in the PM10 mode. Still, we had another set of measurement going on, which was using scanning mobility particle sizer, optical particle sizer, and aerodynamic particle sizer. And as you know that SMPS gives you particle number, which you can convert into mass, assuming some density, up to 700 nanometer, and both OPS and APS can give you particle distribution for size greater than 0.5 micron and up to 10 or 20 micron. So in either case, you can always, combining the two data set, you can create a merged data set which can essentially give you PM10. Of course, you have assumed a particle density which is uniform across the size. And again, what we found that results were quite encouraging for different seasons, for different sites. I'm just showing from one side that there was reasonable agreement between this merged data set from these set of, mainly research grade instruments and what was measured by Plantar PM10 sensor. So we had R square of about 0.75 or more. This is a work which was done to look at, again, the accuracy and precision of gas sensors. And this was done mainly in the cities of Delhi and Mumbai. And we conducted it for different seasons. And we also did a swap out experiment there. Basically, we swapped the sensors which were located in these two cities, but I'm not showing all those results. And these gas sensors were alpha sense make, and they were placed next to gas analyzers, right? That is basically the gas analyzers which are generally part of continuous air quality monitoring system in India and probably elsewhere. So what you see on the left, you have NO2, and on the right, you have ozone. And we found that, well, for a good period of time, there was, again, the sensors were able to match, or using, of course, calibration, sensors were able to provide a close agreement with the analyzer-based measurements. But in this case, of course, we were required to use some advanced machine learning models. In this case, it is not done using linear model. In this case, of course, it was done using certainly a little, more complex model, and details are there in this paper. This is another work which is done by Microsoft Research India, and I found it quite interesting work. That's why I thought I would show it. When you use sensor in the field, regardless of the claims made by sensors manufacturers about its stability or its overall, time period of working, they start malfunctioning after some time in the field, depending on, of course, the MET parameters, aerosol concentration, etc., etc. So a very important thing is that to detect the fault in the sensor, and then that would help you either fix that fault or replace that sensor, right? Otherwise, what would happen that if you don't fix it in timely fashion, then entire sensor may go bad, or you might have a big patch of inaccurate data, which you may not be able to get to use even after applying calibration, right? So these are, in that sense, this is an important piece of work that came out this year only. So what you see here is that there are several examples. What it shows that you look at, there are sensor 7 and sensor 11, and what you see that the sensor 11, suddenly two sensors are placed close to each other, and then we see there is some problem. So these guys actually developed a very interesting tool, basically an algorithm, which can start, which if you run them on these the time series in real time, they could identify that when a particular sensor starts showing some anomalous values. Likewise, what you see then on the right in the top row, you have sensor 17 and sensor 19, and then again, sorry, sensor 17 and sensor 15, and you see that suddenly there are some spikes in the red one, and there's some problem. On the bottom row, what you see here again, in this case, you have orange, that is a reference monitor, reference sensor, and then there is a sensor next to it. And what you notice that on the left, if the sensor is working well, it basically mimics the data, or it has a close resemblance with the reference sensor data across the timestamps it's measuring. And on the right, what you see that suddenly, after some time, when the sensor 9 has some issues in its hardware, then you see the 2 time series start diverging. Okay. So then what they have done here is that, as I said, that they had an algorithm which they can run. If you look at the top row, so you find that they could quite well identify that if a sensor is faulty, that is what you see on the extreme left in the top row there in the plot I'm showing here. And it could identify that, well, the malfunctioning is because of the fault in which component of the sensor. So what you see, the green shows that there is a fault in laser, then orange shows that there is a fault in fan. The blue is actually one which is working, right? So that is the way they, they were able to look at the fault, and then one could, take actions in a dynamic way to fix the problem. Now, what another important conclusion from this work was that you see you have 2 sensors, and on the y-axis you have basically you measure current, and then current is of course calibrated through the factory calibration to give you PM, and in this case of course all about PM. So what they see that 2 sensors, they track very well each other if they are from same make. And on the right, what you see, if they have 2 sensors from 2 different make, so even for identical weather and aerosol environments, right? They both are placed exactly next to each other. All conditions are identical, but you see 2 sensors are responding differently, that is plant, tower, and sensorial. So this also, this point was made in this work, is that the 2 different sensors of course respond quite differently. So therefore even the fault detection in the 2 different make sensors have to be dealt with in a different way. Okay. Let me now briefly talk about this experiment which we have just concluded in city of Mumbai in India. So as I said that the primary goal of this experiment to provide an idea about PM 2.5 sensors accuracy by placing them next to government monitors at 15 locations in Mumbai from November 1, 2020 to May 31st, 2021. So what you see here is that the map of Mumbai, and then there are 5 points, 5 locations that are red there were 4 startups, right? So some developers in the country, in India, they deployed their sensors at 5 locations. So 4 each, so 20 were deployed at 5, and at the remaining 10 sites, which are blue, 2 developers deployed the sensors. So 10 into 220 and 5 into 420, another 20. So altogether 40 sensors were kept in the field next to government monitors for understanding their accuracy and other things for about 7 months. Okay. And remember, Mumbai generally has a high humidity condition. So these are some of the snaps from different locations across Mumbai, and what you see that there are these small supports on which these sensors were put, and then of course you have these government huts where all the reference grade monitors and weather stations, etc. there. So some results I'm showing here now for the season 1, because we saw that actually the calibration model has some drift between the two seasons, because November to January you have one kind of environment even in Mumbai, and February onwards there's some small change. So we have developed one model for what I call as season 1, and then we have applied that model for other locations where we did not have a lot of co-located data. So we wanted to also look into the how well model can be adopted to other locations. Hourly data was used here, and I'm showing mostly results here for PM 2.5. So what you notice first, that this shows the 5 locations where all 4 different sensors were placed, and for 2 seasons. And the very first column, CAAQMS, shows that how many hourly data were sampled across these 5 sites from airport to Mahape. And then other 4 columns show how much data were collected using sensors, and that same thing is also shown in season 2. So what you see that, generally speaking, startups or the developers have a higher uptime than the data collected through the government monitor, right? Generally speaking, maybe there could be some small difference at some places, but overall, if you add that, we have got more data collected through the sensor. So that shows that currently that sensors, if they are kept well, and they can have a very high uptime, which is a very, I think, heartening news. And then once we had that, then we, as you see, we had a 2-phase approach. As I said, that phase 1, and that's still for season 1 only. So you have a source data, then you prepare feature, and then you apply a calibration model, and then you try to look, applying that calibration to the sensor data, how the calibrated data looks compared to the baseline or the government monitored data. In phase 2, we transferred this model, what we call as model transfer, because as I earlier talked about that Gaussian progress regression work, where I emphasize that in the field, there is a need to reduce the co-locations, because I said that co-location is logistically prohibitive, and it could also have other challenges. So idea is that using machine learning technique, if we can develop calibration model which are generic in nature and can work for different locations for different seasons, then you can make the co-location redundant. And that's the idea what we are showing. So then in phase 2, you see most of the things are same, but we have used this model with a long period co-location, and that model is then transferred to another location where we have a very short time. So that means in the long time means we have a co-location for starting November and February. But then we are applying this model to another location where we had a co-location only for, let's say, few days to at the most a week. And that is what the goal is, that you bring it down finally to a 0 co-location. Once you have developed a model and for several locations, then you should be able to apply to at least in that city or in a similar environment to any locations without having the need for a co-location. So we certainly used a variety of machine learning models here, and most of the result, what I will show here is basically using the DNN model. And then as you see that we had the input parameter, which are basically PM 2.5 and 10, then you have temperature, and then to account for the diurnality, you have two trigonometrical functions, and then of course another function of relative humidity. And then we also use PM 2.5 and 10 at previous time steps in the calibration model. And then several non-linear features, as you see, which are product of PM 2.5 and PM 10, or product of PM 2.5, PM 10 temperature and relative humidity. Okay. And this is what are basically what we call different kind of features. Okay. And this is, of course, basically the detailed of the NL model. So let's not worry too much. So this is what earlier I showed, that what's the overall uptime. So you see the first column shows the uptime based on the 7 months data for the government monitor, and remaining 4 columns shows the total uptime. That is basically, as you see, is defined by on time and divided by on time plus off time. So what you notice that all 4 sensors were able to collect more data, had more uptime compared to the government monitor. And altogether we had about 30,000 plus hourly data points. So that's a very large sample where one could play with different kind of machine learning tools and other stuff. And this is what shows basically a snapshot of how the calibrated data looks. So what you see here, the red curves are basically, and so here these are all calibrated with respect to the corresponding government monitor BAM data, and this is shown for all 4 startups. The red is uncalibrated, so you see for uncalibrated, sometime error can be high, can be as high as 40%, otherwise mostly below 25%. But if you apply the calibration, you see for 2 startups at least, the error could be brought down to 15 to 18%. And similarly for those 2 which had superior performance overall based on 32,000 data points, hourly data points, what you see that R square can be as high as up to 0.8 or something. Now here what I'm now showing that how you could bring together each of these elements of sensor-based monitoring, that is basically sensing, application of calibration model, application, bringing the network, then applying the calibration model on the server, and then finally you take the data as an output which can be displayed as graphic or various kind of analytics which you want to do. So this is a full system which we were able to develop as a part of a project, where you see on the left we have used different kind of network technologies. So basically there were like 2G, 3G or 4G, all 3 we have tried and they have been working quite satisfactorily. Then we are also trying this NB-IoT. So I will show that in several cities of the country where NB-IoT network is also on NVIL. And there it would be good to try and transmit the data using this narrow bandwidth IoT network. And in some very small places, for example, in a university campus or a hospital campus or a school, you could use these kind of technologies, which is 6LoWPAN, where you would not need the internet connectivity at every node. Instead, there will be few intermediate nodes which will act as router, and other locations you would only connect them to those intermediate routers, and you will be able to transmit the data to finally to the server. So that is what is shown in this schematic, that through these different network technologies, you can get large volume of the data to the server. And some of the machine learning model, the calibration model, what I showed earlier for gas, PM10 or PM2.5 can give you the corrected data, and that data you can access through APIs, and you can do your own analysis or analytics, or this data can certainly be seen through various portals or through apps, etc., etc. Okay. So that is what is just shown here, that how these different type of network technologies actually are working as a part of particular project I just talked about. Because remember, every sensor generally you can measure the data every minute and probably store it every 5 minutes. So if you have, let's say, 3 parameters, so every 5 minutes you have 3 parameters. So in a day, how much data a sensor is giving? And now if you are storing some other important information, for example, let's say life of the battery or some other health of your network devices and other things. So, and if you think about a city where you have 100 or 200 sensors, then you are actually collecting a large volume of data, and therefore many things are related to how efficiently you could transfer this data. One is that which can cause least burden on the storage and the battery life of the sensor. That's one of the key concerns. And then there are other things also. That's so that the data in a very seamless way, if it comes to the server, then you would have a lot of advantage to do some near real, time analytics and other things. And then finally, it can all be broadcast or can be shared with the concerned audience or the people. And that's the basically overall idea. So this is what is the one test bed which we had here in IIT Kanpur. So what you see, there are sensors, and then there is the BAM here, and this on the right is that the BAM which is shown within the cage in Faridabad, because there were quite a lot of monkeys which used to come and play with BAM, so we wanted to save this from them. And then of course you also see some other devices which are put here, which are some, I think, OPS or something else is there in the laboratory. And this is what was once an unit which was built here. So this is one basically based on some of our own experiments, and in some cases we have also taken from other places. What gives you is a good idea about what are expected statistical parameters one could look for while going for a sensor-based monitoring for PM2.5, PM10, ozone, NOx, SO2, carbon monoxide, and volatile organic compounds. And these numbers, basically what we found or what others are also finding, are in close agreement. So, and basically one should look for this R square, mean absolute error, and it's also good to look at mean absolute percentage error. These three things one should look in combination with each other, and generally one should try to look that they lie within the range which are shown in each of these cells of the table. In addition to that, it's also important to look how closely two sensors sense something, and which is basically sensor to sensor, which we call precision. So the upper part of the table gives you idea about accuracy, because all those numbers are compared to a reference or equivalent reference monitor. And the bottom part of this table gives you idea about how close two sensors measure each other, and that is about precision, and those numbers are also given here. And interestingly, as many of you might be knowing, that US EPA also has given some guideline for the use of these sensors. And you see they are also saying that, well, precision, bias, linearity, and error, and they have given some numbers here, which one should look for if you are looking to have some deployments. So this is just a couple of the network which currently we have. You see one I said that was running in Delhi. Some good number of sensors are still operational in Delhi, which is on the right side of this slide. On the left, as I said, we were running a small network of 25 sensors in the campus of the place where I work in the Institute of Technology, Kanpur. Cost consideration, of course, from India's perspective, certainly in the price of one complete continuous air quality monitoring station, you could have somewhere from 60 to 70, 80 sensors, right? So certainly there is a big difference in the cost, even if you incorporate the maintenance and other costs. So that's the, and I'm sure that almost like between the continuous air quality monitoring stations and low cost sensors, that is the cost basically difference you would see at the most of the places in the world. This is another very interesting example, which is from the sensors deployment in, I think it is in US, Los Angeles. So what you see that they have deployed sensors at 3 locations from a traffic intersection. And what you see that between rush hour, that is this second figure from the left, and non-rush hour, how is the difference between PM 2.5, and likewise how the difference between nitrogen dioxide changes. So these are certainly very, very interesting findings, which can give you a lot of idea about exposure of these pollutants to people. So certainly if there is, right, people who are, have to idle at the crossing, sorry, there is a school nearby, these definitely are very, very useful information. And likewise, there is one that they have done for hotspot analysis, and I believe this is for city of New York. On the left, you see you deploy so many sensors, and then you could understand where the hot spots are. And then also, if you look at NO2, and that shows that curb and roadside, and that can show a very interesting difference, and that difference changes, basically depending on whether you are in an urban location or in a background location, because the dotted line is there at basically 6 in the evening. But the peaks shift, interestingly, between urban and the background location. So these kind of very, very rich information can only come if you have a large network of sensors which are deployed all in very strategic locations. So this is another network we are now working with the government of Uttar Pradesh, where it is, of course, sponsored by Department of State US, where we are hoping to have about 60 plus sensors to monitor PM 2.5 and PM 10 across the city of Lucknow. And Lucknow is the capital of the province or state where I live, Uttar Pradesh. And that is what is the proposed plan that is shown in this figure here. And hopefully we should get this going in next a couple of months. And this is again another network we are ready to put in the city of Jaipur. Some of you might be knowing it's called as Pink City of India, and it is located on the mainly in the westernmost, where you have a reasonable sized desert in Rajasthan, and Jaipur is capital of the state of Rajasthan, and we plan to put a census network of 40 nodes in the city of Jaipur. So what you see here is that the outer boundary in the left-hand side plot is the district of Jaipur, and the inner, this figure shows the city of Jaipur. And the black dot shows the 3. So in this big city, as of now, they have only 3 monitors. And I understand their government is adding 3 more monitors. So they will have 6 monitors. But this district, and this is a very large district and a very large, relatively large city. So, you know, with 40 sensors strategically deployed, certainly can provide a lot more information. What we are. This is, I think I'm going to have, I'll stop in these 2 slides. So this is what we are currently working on, is to use the sensors or use the very high-end chemical information, chemical speciation information, which you get not from the filter-based measurement, which we all are very much used to, instead of using some of these real-time chemical speciation monitoring instruments, for example, mass spectrometer or metal monitor, which gives you every 15 or 20 minute complete speciation of PM2.5. Now, if you have a bunch of sensors and simple sensors, that is low cost PM and some gas sensors, can we train the sensors to pick up some of these source information? Because remember that the first set of instrumentation, which gives you the real-time chemical speciation, helps you find out the sources in near real time. So certainly you get that complete fingerprint and you run some kind of tool. Many of you are familiar, either a positive matrix factorization or some advanced version of that. And then you resolve PM2.5 sources into a variety of things. Some of them can be organics or traffic or something like that, or maybe dust, etc., etc. Now, idea is that whether it is possible to train the sensors which can pick some useful information, and then whether power of machine learning can help us to give the source information in the absence of this spectral data. And you see, interestingly, this is very much a work in progress. We are seeing that for many of the sources, sensors can give you reasonably okay source information. It's not that they are going to give you as accurate, super accurate information, which you get from these high-end systems, but it can give you, as I said, reasonably. Still, you see you have error about 20 to 30%. But remember that in the advantage being that you are not getting only the PM or gas actual status, you also can get some information about sources, and that I think is an added advantage. Of course, this is very much a work in progress, and certainly we should have some more results in future meetings. So, Dr. Verma, I am done here. I'll stop at this slide, and I'm happy to take some questions if you have some time.
Thank you, Professor Tripathi, for your nice presentation. Yeah, there are some questions which I will. The first question is, could the data from the low-cost sensor used for the national regulatory purposes? So, can the data can use the regulatory purposes?
Well, I mean, one has to understand that basically we are talking here about ambient air quality monitoring, right? Your continuous air quality monitoring also gives you data that is only to understand what is there in the air. The ambient air quality data is not used for regulation. For regulation in India, in the context of India, I'm saying, for other places, I'm not sure how it works. For India, continuous emission monitoring system, which are separate systems deployed close to a source, be it a power plant or a chimney or anything, or a treatment plant, that is used for regulations. The ambient air quality data is used to get is collected to understand what's the state of environment. It's not used for regulation. If that is not used for regulation, why would you use sensor data to regulate, right?
But do you think in the future countries may adopt this sensor-based monitoring instead of traditional way of monitoring for the like accuracy or if the quality of data improved? Do you think this is possibility in the future?
You mean whether sensors can augment
Yes,
CAQ?
yes.
Well, I mean, you can better answer. Don't you think that in China already they have a reasonably large network of sensor-based monitoring?
Okay.
I think they have a fairly large, as the slide I showed. I mean, they have a good bit of monitoring going on using sensors. Then I showed in US EPA is using data for different purposes. London has put, I think, hundreds of sensors. How many hundreds, I don't know exactly, but their plan is to put 500 sensors. New York has done. So many cities are, you see how many, the need is that every neighborhood should be able to understand what air they're breathing.
Yeah.
How could you cover that using these reference grade monitors? You have to have a hybrid approach. Now, what would be the model of that hybrid approach? How do you optimize these two different technologies to provide you the optimal data? That's a different story.
One of the participants asked about the validity of sensor-based monitoring data. Is it approved by US EPA if they want to use for stack emission monitoring?
No, these sensors, I think they are not using for stack monitoring. They are not meant for that. For stack monitoring, you still have to have more rugged monitoring, right? Certainly for automobile exhaust, etc., yes, sensors people are using. But for stack monitoring per se, which of course has a very different, concentration, and so that's not useful.
The last question is.
Burma, just tell me how do I just skip from your this WebEx? I'm not able to.
My colleague will escape. No problem.
Just escape it so that I'm not able to just reduce the size of this.
Can you remove him? Stop streaming. Can you remove his screen? Tripathi. There is another question that despite of many types of brands offered by low-cost sensors these days, what need to be considered when we choose a certain kind of low-cost sensors to complement our ground reference station? I think you already answered this question in your one of the slide, but can you just repeat the slide?
Well, I mean, if I believe that if a particular sensor, the best sensor would be, I think, which gives you complete information about factory calibration, which they don't. If you have that information, then I think your job is far easier while you are, trying to calibrate in the field. You understand, right?
Okay.
But that they don't give. Now, in absence of that, I think generally one would see from experience that out of the sensors which are there in the market, at least for PM 2.5, some definitely have a superior performance to others. But that you only come to know once you have tried some in different, different situations in different places. So that comes from little, hands-on experience.
Okay, there is one more question. How to employ this technology to evaluate the sources of air pollution? Source apportionment he was asking.
Yeah, I just said that this is currently we are trying it. It's very much part of ongoing project. But
okay,
idea is that if you have two data set, collected at the same time scale and with same frequency, right? You cannot train sensor with the filter-based measurements because they give you a data in one day and then source information you get on a seasonal basis. So then you don't have the enough data for sensors to train, right? You need a lot of data. That's the first requirement if you want to develop a sophisticated, strong machine learning model. Now, the other set of instruments, for example, aerosol mass spectrometer or metal monitor, I think you know those things, Dr. Verma. So they provide you chemical speciation every 10-15 minutes, right? So basically, in 3 or 4 days, you have enough data to try to get the source information. And then you get this source information every hour. You get this information on the same frequency at which you have collected the actual chemical speciation, right? And at every timestamp, you also have the sensors collected information about PM, meteorology, and gases, right? And probably if you also have VOC there, it helps a lot. Now, this is what you are using to train about sources. That's what we are currently trying. Hopefully, we'll get something.
Okay, we are really lagging behind the time of the schedule. So thank you so much, Professor Tripathi, for the nice presentation. And it was quite informative. So if you have any questions to Professor Tripathi, just let me know. I will pass the questions to him to reply. Now the next presentation is of this model is from Professor Mohammad Bilal from the Nanjing University of Information Science and Technology, China. Professor Bilal is serving a professor at the NUIST, Nanjing, China. He devised 4 innovative methods, namely simplified aerosol retrieval algorithm, simplified merge scheme, simplified and robust surface reflectance estimation method, and aerosol classification using a novel satellite remote sensing approach. He has published more than 90 research papers in top journals, including Remote Sensing of Environment, Environmental Science and Technology, Journal of Geophysical Research, IEEE, TGRS, Environmental Pollution and Atmospheric Science Research, etc. The Jiangsu Provincial Education Department of China has conferred him with a special title of Distinguished Professor based on his outstanding research achievement. In 2020, he was ranked among the top 2% world scientists in meteorology and atmospheric sciences based on his single-year contribution to science. Professor Bilal, the floor is yours.
Thank you so much, Dr. Verma.
Thank you so much. Yeah, we can hear you.
Okay. Can you see my presentation?
No, we cannot say. Can you share?
Okay, just a minute. Is it okay?
It's coming up. It's starting to share content. Yes, we can see. Make it full screen.
Okay. Thank you so much, Dr. Verma, for the invitation, and good afternoon, everyone. Today, I will talk about air quality monitoring using satellite remote sensing. In this talk, I will cover satellite remote sensing product, including MODIS aerosol product based on the dark target and deep blue aerosol retrieval algorithm, visualization and spatial mapping of MODIS aerosol product, MODIS data processing, and validation of Modis aerosol product, and which statistical parameter we should consider during the validation of Modis or any other satellite aerosol product. In the last, I will introduce two new techniques like a simplified merge scheme, which is used to combine different aerosol products. And finally, the simplified aerosol retrieval algorithm to retrieve AOD at local or regional scale at a higher spatial resolution. So in addition to true color images, there are many satellites which can provide direct product of this, atmospheric gases, including nitrogen dioxide, sulfur dioxide, formaldehyde, carbon monoxide, ammonia, methane, and ozone, etc. Currently, there is no direct product by the satellite remote sensing for the estimation of PM 2.5. So, but we can estimate PM 2.5 using AOD information from the satellite retrieval. Although it is not a very simple method, mostly it is a complex and based on the different parameters. Sometimes we can find a linear relationship between AOD and PM 2.5, and so we can predict PM 2.5 at high resolution using AOD. But most of the time we have to consider surface meteorological information, or sometimes we have to add some data from the chemical model to predict the PM 2.5. Also, the accuracy or estimation accuracy of PM 2.5 based on the AOD basically also depend on the region and also depend on the accuracy of the AOD and the resolution of the AOD product. So the PM 2.5 estimation based on the AOD vary from high resolution to the low resolution. So in today's talk, actually, I will mainly focus on the accuracy of AOD product and how to access or process Modis AOD dataset. So in the start, we can see what we can learn from the true color images based on the satellite radiance dataset. So from the true color images, we can get information of cloud, aerosol over land, aerosol over ocean, snow, some data gaps or some sun glint over the ocean surfaces. So these are, even though we can get more information about different land cover types using the true color images data. So now let's come to the our main topic of today, which is the aerosol optical depth. So what is aerosol optical depth? Aerosol optical depth is the measure of absorption or scattering of light by aerosol particles in the atmosphere. It is a total column integrated value from surface to the atmosphere, top of the atmosphere, which does not provide any information on vertical distribution of aerosol. So here is a simple concept of high or low AOD. Low AOD means we have a less aerosol in the atmosphere, or in other words, we can say the atmosphere is clear. And the high AOD means we have a high amount of aerosol in the atmosphere, or we can see there is a polluted atmosphere or polluted sky. So aerosol AOD actually currently available from multiple remote sensing satellite at global scale, like MISR, Modis, Sea-Waves, or VIIRS. So today talk in today talk, I will cover the AOD product from Modis data based on the two different algorithm, like a dark target algorithm and deep blue algorithm over land. So this is a simple process, remote sensing process for the application of aerosol retrieval or aerosol inversion. So initially we have, in the first step, we have a satellite measured spectral radiance data, and then we must have information of aerosol optical properties, which we normally can obtain from the sun photometers network like Aeronet, and we must have knowledge of radiator transfer theory. In the next step, we use this information in the aerosol retrieval algorithm. Before performing any inversion, we normally need to mask cloud or some unusual or abnormal pixel or pixel contaminated by like snow or other surfaces where aerosol algorithm do not perform. So finally, based on this information, we can get geophysical parameters or like aerosol optical properties, aerosol optical depth, angstrom exponent, or single scattering albedo. So these aerosol optical properties are used to in different applications, especially for the estimation of PM 2.5. So this is another journal flow of aerosol retrieval algorithm. In the first step, we must have information of accurate surface reflectance estimation and aerosol optical properties such as particle size distribution, refractive index, aerosol optical depth, vertical distribution, particle size, single scattering albedo, or phase function. So these kind of information we can get from the ground-based aeronet sun photometer network. Using this information, we can apply this information in the radial transfer model. So based on the radial transfer model, we can simulate the top of the atmosphere reflectance, which we can compare with the top of the atmosphere reflectance observed by the satellite sensor to retrieve the aerosol optical properties. So this is a very simple flow diagram for the aerosol retrieval algorithm. So what is the MODIS DT algorithm? MODIS DT algorithm provide aerosol optical depth at 10 kilometer resolution and 3 kilometer resolution over land and ocean. So here actually I'm going to discuss about the DT algorithm at 10 kilometer resolution over land. So in the first step, in the DT algorithm, the pixel are selected just only for the dark vegetative surfaces or dark surfaces based on the TR reflectance at channel 2.11 micron. And the surface reflectance should be between 0.01 to and 0.25. So the pixel which have a surface reflectance greater than 2.5, they are ignored or removed from at these steps. And the remaining pixel are corrected for the gases absorption. So in the next step, pixels are organized into 20 by 20 pixel, or in other words, they are 400 pixel. So from these remaining 400 pixels are masked for the clouds, snow, ice, and other bright surfaces. For example, DT algorithm does not perform aerosol inversion over bright desert surfaces. So these surfaces are removed from the images during these steps. In the next step, the 0.66 or red channel is used to separate the land or water pixel, and also to remove the 20% darkest and 50% brightest pixel to retrieve the aerosol inversion. So in this step, in the DT algorithm, they also remove more pixels which are too dark or which are too bright, so that they can perform accurate retrieval over the land surfaces. So for the highest quality flag retrieval, AOD retrieval, there should be at least greater than 50 pixel out of 120 remaining pixel. And for quality flag 2, 1, or 0, there must be remaining pixel must be like 30, 20, or 12 respectively. So in the DW algorithm also provide the AOD aerosol optical depth at 10 kilometer spatial resolution, but over dark as well as bright urban and desert surfaces. So both of the DT and DW algorithm at this time, they are unable to provide AOD information over the snow surfaces. So in the DB algorithm, same as DT algorithm, pixel are masked for the cloud or some snow ice pixel. And also the remaining pixels are used to calculate the surface reflectance using the minimum reflectance technique. So in case of DT, the first pixel are selected at 500 meter resolution, then they are aggregated to 10 kilometer resolution to perform the aerosol inversion. But in case of DW, the pixel are removed and selected for the aerosol retrieval, and finally AOD is retrieved at 1 kilometer resolution, and then pixel are aggregated to 10 kilometer resolution. So here is the example of minimum reflectance technique, which is based on the climatological data set. For example, if we want to get a minimum surface reflectance image based on the seasonal data, so from each image, from each scene, the pixel with the minimum reflectance are selected to make a one composite image for that season, which is used for the EOD retrieval in the DW algorithm. So along with DT and DW algorithm in the collection 6 of MODIS, the NASA team has introduced another combined product based on the DT and DPU. So basically, the objective of this product is to increase the spatio-temporal coverage of AOD dataset. It means that to increase the to get the pixel at that location where DT is unable to retrieve AOD, for example, over bright surfaces, and and also to get a pixel of that location where DPU is unable to retrieve AOD. So finally, this is a combination of these two algorithm. So when we have to use the DT algorithm or when we have to use DPU algorithm, this is actually defined by the NDVI value. So if the NDVI value is greater than 0.3, then we need to use the DT AOD, and the when NDVI is less than 0.2, which means for the bright surfaces, so we need to consider the DW AOD. And finally, if the NDVI value is between 0.2 and 0.3, and if both of the pixels are available, then we will take the average, or if any of them is available, so we will consider either of one which is available at that location. So DT algorithm provide AOD information at both a 10-kilometer resolution and 3-kilometer resolution over land and ocean surfaces. So here is the example of low resolution AOD from and high resolution AOD from the DT algorithm. So based on the high resolution AOD, we can get more we can check the more spatial variation, or we can get aerosol information at local scale using the DT 3K AOD. So what kind of information we can get based on the AOD? So AOD is very useful to get aerosol information, especially during the extreme events like at different season. So here we can see the aerosol optical depth during biomass burning in winter, and haze pollution and dust storm in summer. And also in spring, we can see the pollution and dust and also biomass burning in autumn season. So we can use AOD to identify the pollution events, to identify the aerosol concentration using during the extreme pollution events. So here I will explain how to visualize near and a real-time MODIS AOD. So we can use the NASA Worldview website to check the AOD for different extreme pollution event, or even though for any day we can get the information of AOD, as well as we can get some other parameter like NO2 or carbon monoxide. There are many parameters in this website. So I will focus only on the AOD information from this website. So to visualize the MODIS AOD, first we need to go this website. Then we have to identify, we have to zoom in for our study area. Then we have to define the date for which we have to visualize the MODIS AOD. Then we have to click on the add layer. So based on after that, we can get this window, and from this window, first we need to search for the MODIS AOD, and then we can select the MODIS AOD product which we want to visualize. So here I select the merge DT and DW aerosol optical depth based on the Terra and Aqua to visualize the AOD. So during the extreme dust storm event, which was observed over Pakistan and India. So here's the AOD during the extreme pollution event over the region. So this is basically a conversion of satellite radiance from satellite radiance to the MODIS aerosol optical depth. So from this website, actually there are many parameters. I would like to show different other parameters which we can observe, identify from this region. Like let's go for the same dust storm event. So here we need to add on the add layer. Click on the add layer. We can check for the MODIS AOD. So here's a MODIS EOD based on the different parameter, and we can also check the MODIS deep blue aerosol angstrom exponent and EOD based on the different parameter. And also, if we want to check the VS EOD, VS EOD is also available from VS dataset. Actually, VS is launched after for the recent year. We can check for the VS. EOD from OMI sensor, and also I'm not sure why what is the going from. So here is the we can check the VS nighttime light, and also we can check for the VS aerosol optical depth, VS fire and thermal anomalies, brightness temperature, and VS deep blue angstrom exponent. And we can also check actually aerosol types based on the VS data from this website. So here is aerosol types. So here is the information of aerosol types based on the VS data. So we can see there are some smoke over the region, some mixed aerosol coarse and fine aerosol. So this website is very useful to visualize the near real-time data based on the different sensor, based on the different parameters. So in the next step, I am going to do the spatial mapping of MODIS EOD based on the Giovanni data. So in the NASA worldview, we actually can get the near real-time visualization of MODIS EOD, but here you can make a spatial map based on the long-term temporal data set. So here is same like the NASA worldview. So here we can search for the MODIS EOD. Then we need to select the MODIS EOD for the dark target or whatever you want to see. Which you can also get the NO2 data or SO2 data based on the different sensor like OMA data. So I just check for the MODIS EOD. So then you need to define the time select the plot, which type of plot do you want to make. Then you need to select the define the dates. Then you have to define the study area, and you can plot this map. So this is a spatial map of MODIS EOD for three basically it is the average of EOD based on the three months data set. So you can also save this data set in GOT format or KMZ or in PNG format. So this is an image which we can make from the Giovanni dataset, or you can also use this website to do a spatial comparison. Like normally nowadays people are doing some comparison studies before and after COVID. So this website is very useful to perform a spatial comparison before and after COVID or for any event. Like there is a fire activities, biomass burning activities. So you can use this website to see the aerosol concentration before biomass burning, during biomass burning, as well as after biomass burning. So this is very interesting, a very good website. Now I will explain how to download the MODIS dataset from the LATS website. Basically here you can get the from the Giovanni. Actually, this is based on the MODIS level 3 dataset at 1 degree resolution. But for the MODIS level 2 dataset at 10 kilometer resolution or 3 kilometer resolution, you can get data from this website. So first we need to go to this website, and then we need to log in or make a if we need to register if we don't have any login information. Then first we need to define the sensor if we want to get the images for the Aqua or Terra. Then aerosol product. This is level L2 means the level 2 data at 10 kilometer resolution, and 3K means the MODIS EOD information at 3 kilometer spatial resolution. And then we need to define the time for which we need to get the MODIS data product. We can order for the long time period, but we should be considered that we cannot order files more than 2000 in a single order. So we have to define the time and date so that we can get the file less than 2000 in a single order, but we can get order Modis dataset for different small time period. And in the next step, we have to define the spatial region for which we need to get the Modis aerosol data. And the second, we need we can see all the available files for the Modis AOD product. Then we need to select all and review the order and submit it. So after that, we can get the email from the NASA server, and when the data is ready, we can download from the server. So here is a example of Modis data processing. You can use many different tools. You can use different programming language. So I normally use Modis conversion toolkit for the Modis data processing. So here is the example how to process Modis HDF files. So first we need to input the HDF file. We need to select the projected dataset. Then we need to define the output path and file name. Then which dataset you want to process. You can select multiple dataset. I just select only one. Modis combine TT and DW AOD product. Then you need to define the projection and datum, and finally you can process it. So using these steps, you can get the projected dataset from HDF file, which you can use in any image processing software like a NV, or you can use in the RASMagen or ArcGIS to make a spatial map. So for the validation of Modis AOD product, we normally use the ground-based AeroNet dataset. So AeroNet provide high temporal spectral AOD measurement, but at a point location. So which are normally used to validate the satellite AOD product. So for the validation of satellite AOD product, we normally consider few statistical parameters like a Pearson correlation, slope and intercept, root mean squared error, relative mean bias, and the finally, which is most important parameter, is expected error. This is expected error of Modis DT algorithm over land. So what is mean by the expected error? Expected error means the data set, the AOD retrieval should be the upper and the lower envelope of the expected error. If the data is between these two lines, we can say that the satellite has a very good aerosol retrieval algorithm, and the quality of the AOD is very good, and we can use it for further research application. If the data point outside these 2 points is not a good quality, and if we use that data set for any other research application, for example, for the estimation of PM 2.5, so it may lead to a significant error in the PM dataset. So here is an example of validation of Modis AOD over Hong Kong International Airport and the City University of Hong Kong. So actually, I will focus only on the right panel, which is the validation of Modis AOD over Hong Kong International Airport. So here, if we look at the correlation is 0.79 almost, which is a very good correlation for the validation of AOD. So if we only look at the correlation, we can say that the Modis AOD product is very good. It is following the same spatial temporal variation as the ground-based sun photometer data. But if we look at the data points here in this panel, if we look at the dotted orange line, these are the expected envelope. This is the lower envelope, this is the upper one. So lower boundary and upper boundary. So all these points are outside the lower boundary. It means that the Modis, although the Modis algorithm is showing the same temporal variation as a sun photometer dataset, but it is underestimated, significantly underestimated for the low as well high AOD for high AOD values. It means that the over the Hong Kong airport, the Modis algorithm has an error in both surface reflectance and aerosol model, which is used to retrieve AOD in the inversion algorithm. In case of surface reflectance, it is showing that the surface reflectance is overestimated by the algorithm during the inversion method, which leads to a significant error, a significant underestimation in the data set. So here This is a very good example to understand that we have to consider actually not only the Pearson correlation, but we must consider the expected error whenever we need to evaluate the MODIS or any other satellite AOD dataset. So this is another validation of the MODIS collection 5 and collection 6 dataset over Pakistan. We have two aeronet sites over Lahore and Karachi. And here we can see that there is another term like a relative mean bias, which indicate that actually the overestimation and underestimation. If the value of RMB is greater than 1, it is showing the overestimation. If the RMB value is less than 1, is showing the underestimation. So in comparison between collection 5 and collection 6, the overestimation is reduced by the collection 6. And in case of over Lahore, in case of Karachi, also the relative mean price is, or in other words, overestimation is reduced in collection 6 compared to the collection 5. But in case of DW algorithm, actually over both sides, the underestimation is increased in the collection 6. It should be supposed that in collection 6, the retrieval accuracy should be higher than the collection 5. But actually here the underestimation in the collection is more as compared to the collection 5. So keeping in this validation, we also validated collection 5 and collection 6 product over mainland China or different region, and we have observed that based on our investigation and based on the investigation from other researcher, the TT algorithm is normally they overestimate the AOD and the DW AOD is underestimated compared to the AeroNet dataset. So keeping in this mind, we have introduced another merge scheme, which is simplified merge scheme, which is used to combine DT and DW algorithm to make a new data product. There's one product which is available in the NASA from NASA team, which is defined based on the NDVA value. But in our case, we did not use any NDVA value. We just used this criteria. If the DT AOD exists, then we will use DT AOD. And if the only DW AOD exists, we use DW. And if both are exist, then we will take the average of these two. But we should be noted that for these one, we must have to use the highest quality AOD retrieval. Otherwise, it may lead to any error in the data set. So using this criteria, so what we can get more number of spatial pixel and temporal observation for the DT and DW AOD. So to test this technique, we have selected different sites located in Asia, Africa, Europe, and North and South America at global scale. So we have validated these TT simplified merge scheme and compare with the MODIS collection 6 TTP dataset. So the first two panels showing the left panel of the DT collection 6, DTP collection 6, and the right panel are the DT SMS based on the simplified merge scheme. So the first two panel are the validation over Asian side. Second is the lower bottom. The one is the over African side. Then the third one on the right is the over European side, and the last of the bottom one is the on the right side is the over North and South American side. So for each side, we can see that the number of retriever within the expected error is increased for the simplified merge scheme over all the sides, and also the number of observation or co-located point are also significantly increased. For example, over Asia, it was around 5,200 for the DTV, but in case of simplified merge scheme, increase from 5,200 to 6,800. And over African side, it is almost increased by 600 points. And over European side, the number of located points for the same time period is almost increased by 7,000 points. And over North and South American point, the number of co-located points increased from 8,000 to the 70,000. It is almost 9,000 points. We can get more observation using the simplified merge scheme compared to the MODIS DTP combined merged data product. So it has a good accuracy compared to the DTP NASA AOD product, and also it has a more spatial temporal coverage compared to the DTP product. So in the next step, we have validated this scheme over different land cover types, like when the NDVI value is less than 0.3, between 3 to 0, and greater than 0, more dense vegetated, moderate vegetated land surfaces, and over bright land surfaces. We have compared and validated these surfaces. Again, we have observed high number of retrieval within the expected area in case of simplified merge scheme compared to the collection 6, and also collection 6.1 dataset, which is improved compared to the collection 6. And also the number of observation increase in case of simplified merge scheme over all the land surface type, which is also in favor of in our new technique, which can be used to merge different aerosol product to make a new composite product for the to increase the spatial temporal coverage. So again, to test this simplified merge scheme, we develop a new, we generate a new product at 3 kilometer resolution using the DT and DW dataset, and compare with the DT AOD at 3 kilometer resolution. And we validated this dataset over the European side. For example, in case of Paris, we can see that the number of retrieval within the expected error were only 8% in case of DT AOD at 3 kilometer resolution. But in case of simplified merge scheme at 3 kilometer resolution, the number of percentage of retrieval increased from 8 to 63%. And also the root mean scalar increased from 0.36 to 0.18. Overall, the number of observation also increased. The percentage of, or in other words, the quality of the retrieval also increased using the simplified merge scheme. So recently, we used this simplified merge scheme to generate a Aquaterra TTB aerosol product over Pakistan. So in the first step, we generate a DTB OD based on the DT and DW algorithm for both Terra and Aqua separately. Then we used these two dataset, Terra and Aqua DTB, to make a merge Aquaterra AOD. So in case of Aquaterra, same like a DT and DW AOD. If AOD is available from Aqua, we will consider it. If it is available from Terra, we will consider it. But if AOD is available from both of them or either of them, then we will, if both of them, then we'll take average, same as we did in the first step to generate a DTB AOD. So in this case, what we can get a higher spatial temporal coverage in case based on the DT and DW algorithm, and also based on the Terra and Aqua AOD, because both have a different spatial coverage due to the cloud cover. So we can make a very good composite of AOD to represent the air quality conditions over the region. So using this Aquaterra MODIS DTB AOD, we have characterized extremely polluted cities to the low polluted city over Pakistan. So we have selected almost 80 cities. So for 80 cities, we have get the AOD, and we rank them from extremely polluted to the least polluted cities, as we can see on this map. And then we have also in this on the left hand side figure, we also characterize the city, and also we identify the number of available valid pixel for the AOD for each city, which vary from city to city. Normally, we have a less pixel over the southern area, southern province, due to the bright surfaces, desert surfaces, where DT algorithm is unable to provide the AOD pixel. So the third panel is showing the AOD variation, monthly variation over the for all the cities. Here we can see that most of the cities are polluted or are contaminated by aerosol during the summer season, which is probably due to the high dust storm events over the region. And we can also see some high value in October and November over some most polluted cities, which is normally linked to the biomass burning or crop residue burning over the region, which also affect the air quality of the region. And finally, the lower panel is showing the long-term AOD variation, annual variation for each city from polluted to the low polluted cities. And we can see that all the polluted cities, almost, or most of the cities, are continuously polluted from 2003 to 2017. So the AOD value is extremely high, greater than 0.6. This is the annual average value, which is too high for the for all the cities. So it means that overall the condition aerosol loading or over this region is very high, and most of the cities are polluted with the aerosol concentration over the region. So here's the interesting results what we have observed in this research. We have found that the spatial distribution of MODIS AOD is linked to the spatial distribution of nighttime fierce light data. So wherever we have a high radiance of light, we observe a high value of AOD. So we can see the same pattern as the nighttime lights, it has the same pattern as the AOD. Also, we have the same pattern for the land cover types like vegetation and urban area. So these two parameters are very important, and we can link these two parameters to identify the hotspots region and to identify the main cause of the poor air quality over the region. So in our previous slides, we have learned about the MODIS AOD at 10 kilometer, at least 10 kilometer spatial resolution based on the DT and DW algorithm. So here I will talk about the simplified aerosol retrieval algorithm, which can be used to retrieve high spatial resolution AOD at local or regional scale, especially whenever we have a very extreme pollution event. Because for the extreme pollution events like a haze pollution or dust storm, the DT and DW algorithm are unable to provide the aerosol information. But fortunately, we have a SARA algorithm which is able to provide high aerosol information during the extreme pollution event. So this is a simple algorithm. For this algorithm, we need some information of the geometry like a solar and sensor angle. We must have information on the top of the atmosphere reflectance and surface reflectance, and these information are used in the radiative transfer model equations finally to retrieve the aerosol information. So here is the example of the extreme pollution over Hong Kong and China. Here we can see that the panel A is showing the SARA AOD at 500 meter resolution, and here is the MODIS AOD at 10 kilometer resolution in the panel B, which is unable to retrieve high AOD information during high aerosol loading over the region. And the third one is showing the detailed information at district level of over the Hong Kong region. So using SARA algorithm, we can get we can get more variation. We can check more aerosol variation at local scale. So this is a very good example of SARA AOD at district level to see the spatial variation of aerosol optical depth. So here is another comparison between SARA and the MODIS DT and DW algorithm during an extreme dust storm event over China. So this panel is a true color image. This is showing the spatial distribution of dust storm and also cloud. And here the panel C is showing the DT algorithm, which is unable to retrieve aerosol information because during the dust storm there were very high AOD was there. So DT algorithm was unable because it mixed aerosol content with the cloud and mass in the initial pre-processing, and these pixels were removed during the pre-processing steps, and the DT algorithm was unable to retrieve the AOD. The same case in the DW algorithm, it has a more pixel compared to the DT, but it was also unable to retrieve the AOD information. So here come to the panel B, which is based on the SARA. We can see that SARA has ability to retrieve AOD during the extreme pollution event like a dust storm, and we can see that it's showing the more spatial variation in the dust storm. We can identify the different high AOD region based on the SARA dataset. Here is another example of AOD comparison between the MODIS and SARA. This is comparison with the collection 6.1, and also I include the MODIS DT AOD at 3 km resolution for the comparison purpose. So the panel A is showing the true color composite based on which is showing the clouds as well as the haze pollution, and this is a cloud mask from the MODIS. We just plotted this cloud mask to show to confirm that this is not a cloud, this is a haze pixel. So this is also confirmed by the MODIS cloud mask, and so it means that if it is not masked by the MODIS algorithm, so there should be the aerosol pixel there, but unfortunately MODIS DT algorithm at 3 km resolution, MODIS DT algorithm 10 km resolution, they both were unable to retrieve AOD or during this extreme haze pollution event over China. Although MODIS D Blue has some pixel, but there is very less variation in the haze phenomena over this region by the D Blue algorithm. But we can see that SARA again has ability to provide AOD information during the haze event at local or regional scale. So for the local or regional scale high pollution event, the SARA is a very good algorithm to be used for to check the aerosol information. So in the next step, we have used SARA AOD, and we develop a linear relationship based on the surface meteorological data set over Hong Kong and PRD region. And we developed this linear regression model based on the AOD to estimate PM 2.5 at high spatial resolution over the China. So here is the spatial distribution of PM 2.5 over Hong Kong and over China, and also there is a local variation of PM 2.5 at local scale over the Hong Kong. In the next step, we have also tested the SARA algorithm to retrieve AOD at 2 meter resolution using the worldview dataset, but only for the shadow pixel. So this is a true color image. From this image, we masked all the bright surfaces and just get the shadow of the buildings. And using these data set, we applied the SARA algorithm to retrieve the AOD at 2 meter spatial resolution. So this is the today talk. Thank you so much. If you have any question, I would be happy to reply you. Thank you so much again.
Thank you, Professor Bilal, for your nice presentation. It contained a lot of new informations. There's already a question from participants. How can we ensure that the AOD reach to the ground? Should we calibrate with ground measurement PM 2.5 or only with aeronet AOD? That means he or she want to know the comparison of AOD and ground-based measurements.
Actually, first for the satellite AOD, first we need to check the quality of the AOD retrieval. For this, first we need to validate the AOD dataset based on the aeronet AOD measurement or any sun photometer dataset. So first we need to investigate this one. The second, if we want to get any relationship between AOD and PM dataset, so as I mentioned that sometimes over some region we can get a linear relationship, and definitely it's also depend on the season, because in over Hong Kong I found that only AOD can be used to predict 70 to 80% PM 2.5 in autumn and winter, but there is no relationship between AOD and PM 2.5 during spring and summer season. So it's very, so sometimes we can use only AOD to estimate PM 2.5, but most of the time we have to consider other parameter like a surface meteorology, like temperature, relative humidity, specific humidity, or planetary boundary layer height. And also sometimes we have to use some chemical model to, or some other tool like a geographically weighted regression model or some machine learning technique to predict the PM 2.5. So first we have to check the quality of AOD, whether it is accurate or not.
Okay. Any other question from participants? please write on the chat box. Sorry, Q&A box, not chat box. There is some technical questions. What does mean by RMB and RMSE?
Actually, RMB is a relative mean bias, which is calculated based on the average value of MODIS or sun photometer data set. So the normally there is a simple equation first we need to subtract MODIS Aeronet AOD from the MODIS AOD and divided by the Aeronet AOD. Actually, I give the reference there. From the reference, the equations can be obtained. It's a very simple to calculate, but it is very important parameter for the validation of AOD data set. So this RMB actually indicates the overall overestimation or overall underestimation in the AOD data set. As I mentioned that if the value is greater than 1, so it is showing the overestimation. If the value is less than 1, it is showing the underestimation in the AOD data set. And root mean square error is basically showing is represent the scattered point. The low value mean all the data set is close to the 1 line. If the value is high, it means we have a more scattered point in the scatter plot. The data are very far from the 1 line. It means that if the root mean square error is high, it means that the retrieval has very low quality, and the percentage of retrieval within the expected error will be less. So this kind of data set is not recommended to use for the estimation of PM 2.5.
Okay, I think there is no question from. Oh yeah, how can we combine sensor network data with satellite data for a city? I mean the presentation which we have before you and your presentation, how we can combine the sensor based monitoring and the satellite based monitoring.
Actually, there are many techniques like data simulation. Now people are using, they are using ground-based data, they are using model data, and they are using satellite data to combine them to make a new product. So data simulation is a very good, I would suggest a very good example to combine sensor-based and satellite remote sensing data set. So data simulation, people are using this one. They are using ground-based sensor, satellite data, as well as model data set to make a fusion or data simulation to get a new product.
Okay. Thank you so much. No more question now. Thank you
Welcome.
for
Thank you so
your
much.
very informative presentation. If anyone have any questions to Professor Bilal, just let me know. Write to me. I will pass the questions to him and he will reply to you later. So now we move to the last presentation of the day, that is fourth presentation on air quality monitoring module, that is the continuous emission monitoring system by Dr. Sirakan Liang Sakul from the Department of Industrial Works, Thailand. Dr. Sirakan is a director at the Air Pollution Section, Industrial Environmental Technology Promotion Division, Department of Industrial Works, Thailand. She is involving in development of many guidelines and air emission standards, such as Code of Practice for Petrochemical Industry, aiming to reduce emissions of VOCs from the storage tank, flaring and shutdown or turn around activities, power plants, air emission standard, and continuous emission monitoring system requirements and APRTR requirements for the industrial sector. Dr. Sirakan, the floor is yours.
experience in let me take a few moments to share the slide with you.
Yeah, sure.
All right. Can you see my presentation?
Yeah, we can see. Hello, we cannot hear you. Are you speaking? Hello. We cannot hear. Maybe the weak internet. No. Hello. Can you hear me? We cannot hear you. Huh? But our connection is quite weak, I think. Can you unmute yourself? You are muted. Hello. Yeah. See, already our connection is weak. Hello, Dr. Sarakan. We cannot hear you. Can you unmute?
Dr. Verma, can you hear me?
Yeah, we can, but
You can hear
I
me,
think
right?
if you can switch off your video, I think things will be improved.
All right.
See, just off the video, and I think start from the beginning. We cannot hear you. Hmm? Hmm.
Hello. Oh.
Yeah, we can hear you now.
All right, that's good. So
Can you start from the beginning?
the same implementation we first covered the Rayong area. So I like to give you a background of Rayong province.
Okay.
So the Rayong province hosts majority of petrochemical industry. So the industry not only bring jobs but and prosperity to the country, but also air quality degradation to the area. Over the early year, we have seen air pollution on the rise. At the same time, the government tried to develop regulatory tools to mitigate the problem. And since 1992, we have EIA, which is required for the major industry to limit emission from such industry. And then later, SEMS came along mainly to monitor the emission of bacteria pollutants, such as oxides of nitrogen, sulfur dioxide, and particulate matter. So since 1990s, air problem in Madhya area, Rayong province, has become the main conflict between the industries. So Ministry of Industry introduced SEMS and requirements such as industry and power plant as other industry that require to perform EIA report to install SEMS. We focus on the Madhya area and its vicinity, which cover 4 industrial estates, namely Madhya Industrial Estate, Padang Industrial Estate, Eastern Seaboard Industrial Estate, and Asia Industrial Estate, which you will see on the map that these 4 industrial estates located closely in the area. And this actually bring the problem to the area of Madhya and its vicinity. At the beginning, we didn't have a data center to collect the SEMS data. But later in 2007, Department of Industrial Works established a data center and these factories to send SEMS to the data center. We also have another authority, which is Industrial Estate Authority of Thailand, who oversee the factory inside the estates, as well as developing an industrial estate in Thailand. This authority, I would call in short IEAT, has ordered all power plants located in the industrial estate throughout the country to install SEMS and send data to data acquisition. This once we receive the SEMS data, we have a staff to look at the SEMS data to check whether it's if there is no data coming in, we would contact the factory to check the system, or if we see that there is a irregularity, they would contact the factory as well. The factory is required to send monitoring data at the standard condition, which is at 1 atmosphere, 25 Celsius, and 7% oxygen content. However, SEMS alone does not help to reduce the air pollution crisis in the area. Therefore, in 2009, National Environmental Board has to declare the whole area of Madhya and its vicinity, including its shoreline, as pollutant control zone. This gives authority to the provincial mayor. Provincial mayor can impose stricter standards and extra measures for coping with the problem in the area. With SEM notification, currently there are 36 stacks from 29 industries submitting data to the center. Most of them are from petrochemical industry and from combustion process. Not only the factory has to comply under MOI or Ministry of Industry notification, but also they have to comply with other requirements, such as AEAT requirement or EIA and factory permit conditions. Some are voluntary, submitting SEMS data to the center. But if you look closely, most of this that come from a combustion process. And we have the data center, which is open to public. The pin that you see on the map are the location of the industry that has installed SEMS throughout the Thailand. You see that mainly located in the central part and the eastern part of Thailand. And for the rest of the country, mostly are from power plant. We have seen some benefit of SEMS itself, such as the factory can use SEM as self-monitoring for air emission and for process optimization control. If the emission deviate from the normal value, it serves as an early warning. This in turn makes factory a better compliance. And by displaying emission information to the community, it reduces pressure from the community. They can start talking about the numbers instead of guessing the number by their feeling. Once the public can access the information anytime, the industry in the area are gaining trust from the community. And it also increased communication effectiveness. However, the factory are still required to perform stack monitoring by conventional method twice a year. Currently, Ministry of Industry is considering revising SEMS notification to include quality assurance requirement in order to recognize SEMS as a full standard method. A proposed rule will cover the whole country for 13 groups of process or industry. We have a basis of thinking that from the Rayong Mataput area, once we want to expand to cover the whole country, we don't want to make a burden to the industry. As you well know that SEM is very expensive. So a small industry really reluctant to spend the money on SEMS, especially during this time when we have the pandemic, that the money are spending on the health issue. So we are targeting only 20% of the high risk industry. That means that we can cover the major industry that give the, or we can say the big polluter. So we catch a small fish, or we catch a big fish instead of catching out 80% of a small fish. The proposed draft will cover the power plant with capacity greater than 29 megawatt and boiler capacity greater than 30 tons of steam per hour, or heat source capacity more than 100 million BTU per hour. For the cement production, it will cover the factory that has more than 3,000 tons per day at the stack from clean and clinker cooler. For the power production, it will cover the factory with capacity more than 50 tons per day at recovery furnace and lime kiln. For petroleum refinery, it will cover the fluid catalytic packing unit or FCCU and deep catalytic cracking unit, or DCCU, full oil combustion unit, and sulfur recovery unit, or SRU. And it will cover the production of iron steel that has greater than 100 tons per day at the smelter furnace or any preheat unit using oil or coal as heat source. For the production of other metals, it will include the factory that has capacity greater than 50 tons per day at the smelter furnace, and the production of lead greater than 10 tons per day at the furnace. For the waste incinerator, it will cover all sizes of industrial waste incinerator, but it will only cover the municipal waste or infectious waste incinerator that has capacity greater than 10 tons per day. For sulfuric acid production, it will cover the factory that has total capacity greater than 100 tons per day. For gas production, it will cover the factory that has heat input greater than 100 million BTU and other units that required by EAA. For the parameter that we are interested in, mainly oxide of nitrogen, sulfur dioxide, and particulate matter. For other parameters, it will cover air flow rate, oxygen content, and CO. So that's all would be my presentation. It's very short, but however, I would like to give you more chances to have a questions so that I can answer according to your interest. So thank you very much for your attention.
Thank you, Dr. Sirakan, for your nice presentation on the continuous emission monitoring system in Thailand. It was quite informative. So may I request the participants, if they have questions, please write in the chat box, or sorry, in the Q&A box. Does anyone have some questions to ask about the continuous emission monitoring system? Yeah, there is a question. The policy to share CEMS data for research. Is there any policy to share the data for research?
We have the Information Act in Thailand, which the academia can request for data sharing. But however, currently we share the information to the public online only, or if that include the company name. But for research purpose, we are able to share that information as well, but we have to blind the name of the company.
Okay. There is another question that the proposed draft is applied only during the COVID-19 pandemic?
Oh no, we are drafting now, but we will give a lead time for the industry about 3 years. It's not yet finalized, which we hope that by the end of this year or by next year, we will be able to finalize the draft. right now we still have dialogue with the industry, so it's still ongoing. And so after that, we give a lead time about 1.5 years to 3 years, and then we'll implement for the whole country, so
Okay.
that the industry have time for installation.
How are you validating the data of CEMS?
Yeah, and currently that is the problem for us. That's why we still ask the industry to perform a conventional gap sampling method by a standard method twice a year to verify that the information that they send to us is comparable to the standard method. However, for the new draft, we will include the data assurance in there as well. But we are still thinking, because doing the data assurance is quite costly, which we estimate that it will be about 300,000 baht Thai, which is about 10,000 US dollars per performing of data assurance. So we're still discussing about this.
Okay.
I noticed someone asking about the gas, the standard gas, right?
Yeah.
We don't have a standard gas available in Thailand, so we have to order from USA, which that's why it's so costly for us.
Okay. And are the proper US EPA calibration gases available for RRC.AP?
Can you say it one more time?
Are the proper US EPA calibration gases available for RRC.AP?
Yes, we still looking at the method that we understand that there is availability of the standard gas from USA. For example, a single gas standard.
Yeah, there is
Yes.
another. Any economic impact study on the draft regulation?
In Thailand right now, it's required us to study economic impact before sending a draft to the for consideration. Yes, we still have that left that we need to perform before submitting this draft.
Okay.
But that's why we have a dialogue with the industry, because the industry itself right now they are looking at the cost of the system as well, that how much it would cost. So we estimate based on a type of industry. For example, for petrochemical industry, right now, because of the condition of the factory that is required to be explosion proof and so on. So right now it's estimated to be quite very expensive.
Yeah, there is a question from Ithipol from PCD. The CEMS system is very advanced system to monitor the emissions. My question is that there any support from the government, since the CEMS system is very costly?
Right now, for the we have the program from the Board of Investment that for installation of the equipment for the environmental purpose, that the company can ask for a tax break, the import tax break. Other than that, I'm sorry that we don't have other kind of monetary support for the industry.
Okay. How many CMS are actively providing data on the online system?
You mean right now?
Yeah.
Right now, we have 306 data sets that are coming in from 138 factories. So mostly from the central part and eastern part of Rayong province.
Okay.
And those that sending in the data to us will be available on the online from the website that the public can access 24/7.
Okay, if there is no question further, yeah, I think so. There is no. Huh? No, we don't have. Let me check further. Check. No.
There is question from Saket Kumar for is there any SOP for validation of SEMS data? We follow the US EPA guideline, but so we are still looking into the procedure, whether it's possible or not to be done in Thailand in terms of not only a technical but also the cost as well, whether it's the Thai industry can perform according to the US EPA guideline or not. So we're still discussing whether we will follow part of it, and we might, how can I say, reduce some of the burden for the industry, but still in acceptable quality for the data auditing.
Okay, are alternative work procedure such as predictive emission monitoring system evaluated? PEMS system evaluated?
For PEMS itself, some industry has introducing PEMS, but however, we still not yet study into the detail of PEMS, because I understand that it will vary from one type of industry to another type of industry. So that we look into this alternative as well, so that for the industry that is ready for PEMS can utilize the PMS instead of CEMS.
Okay. Do you have posed any criteria for stack testing teams, such as accreditation according to ISO 17025?
Yes. Let me say this: for a conventional method, the testing company has to be has to register with us, and also must be qualified with ISO 17025, right? Yeah, 17025 standard. But for SEMS itself now, we haven't been certified to any company yet. So, but basically, the company has to be certified with ISO 17025. Yes.
Okay. Further question. Okay.
Another question is the low-cost sensor.
Can DIW support or interest in low-cost sensor installed nearby community as local warning tool?
Actually, there is another organization such as IEAT, Industrial Estate Authority of Thailand, which they run the industrial estate. They are very much interested in low-cost sensor, and I think that they install some of this sensor in the area so that they can monitor the quality of the air quality in the area. Yes, we some of the authority in Thailand already implemented that.
Okay, I think no more question now. Okay, no more questions. So thank you so much, Dr. Serakan, for your nice presentation on the CEMS. It was very informative. So if anyone have some more questions regarding this CEMS, just let me know. Please write to me. I will pass the questions to her, to Dr. Serakan for answer, and she will reply you later. So now we have come to the end of the presentation on the air quality monitoring module. This is the end of today's session of the capacity building workshop on air quality monitoring. Thank you to expert speakers for your presentations, which were full of new informations and knowledge. I believe all participants will benefit from the knowledge you shared. We are thankful for for your contribution to the workshop. Thank you to participants for joining the session. It was a long session, and thank you for your interest and passion. Please join tomorrow at 1 p.m. Thailand Standard Time for the second session of the workshop, that is Module 2 on emission inventory development. We will upload the PPTs of today's presentation on the workshop website. Please visit the website of the workshop for reading materials relevant to today's presentation. Also, please provide your evaluation feedback for today's session. Remember, evaluation feedback is needed for the certificate. You may submit the evaluation for whole workshop at the end of the workshop. It would be great if you provide feedback after each session. Otherwise, you will forget the content of the presentation. Thank you again. Have a nice evening and stay safe. Thank you so much. So, Bayasa.